I said to take a photo. Oh, actually, go to the next slide, please. Yeah, I have to take a photo.
Okay. Stand in front of the slide.
Listen to the photo or
Whatever you want.
Yes, we did.
Do you center yourselves? Center yourself in the projector
Move towards the table.
and then move forward so your legs are tapping the table.
That's not it. If you like each other.
Yeah.
Okay, so you should be able to see.
I'm listening to it.
Okay.
I know, so much. That's like a mouse. Okay, 1 minute.
Are you like still setting something up, or should I?
Just be like,
So keep still.
Oh, cool. What?
I mean, what is coming? What's that's been here since yes, when you were great, Nicole.
We good to start?
Okay.
All right. So our design goals for the separation system were to hold the sustainer and booster together throughout the boost phase until staging, and to positively retain the sustainer to the booster, and then after burnout to separate the sustainer and booster both mechanically and physically, creating a distance between them, and to protect the booster from sustainer ignition and the sustainer's exhaust. Throughout our preliminary design process and research and development, we came up with this set of potential designs, and we rated each one of them in 1 through 5 in each of these categories. For like higher score means lower mass, volume, and complexity, and a higher reliability, testability, and booster safety. 3 of the designs tied the highest score, and we chose the two of those that were the most dissimilar from each other to move forward with development on. And
the first of these designs was the cable cutting design, which would use a monofilament wire such as fishing line, which in some preliminary calculations turned out to be about wire weight rated to be about 70 pounds, which would be wound up and through the sustainer motor retainer before coming back down and fastening to a plate above the bulkhead. And then we would also have linearly actuated blades, which would cut through the wire at the separation point in the rocket's flight, and 3 total of these spool blade assemblies located around the circumference of the booster to distribute the force loads. As you can see in these photos, this is a rough mock-up of a spool that the wire be wound upon. It's tapered on one side to allow for easier respooling and wiring when you're initially attaching it, and just to make sure that the wire does not get caught on the axle. These linear actuated blades would either have been through a pressurized mechanism, which we'll get into later, which is a bit of a safety concern, as well as another alternative would have been on a servo, which would convert rotational motion to linear motion. As for why we decided not to move forward with design, again, those safety concerns and reliability with having to simultaneously cut 3 separate wires. If only 1 or 2 of them got cut, then it may not fully separate the rocket. Integration would be challenging because you have 3 separate wires that you need to all tie down in a very small space at the same time, while having the sustainer portion in a close contact with the booster portion, and then difficulty to actually manufacture space for these wires to be fastened.
The second design that we decided to move forward with was our taper lock position design. In this design, the sustainer would have a tail cone attached to it, and there are a set of 3 radially symmetric pedals that that expand outward and grab onto the inside of that tail cone and create and there's a flange that they hook onto. It's similar to a machine tool holder in the way it creates a locking force. The linkage geometry to which the pedals are attached creates a vice grip like locking effect to hold those pedals in place. And it's a single actuation to release the system. As the piston moves up, it forces the pedals inward immediately before it applies an upward force onto the stainer to physically separate the two stages.
So we have this animation here illustrating how the whole thing works together. So obviously there's a lot going on here. So to help walk through it, we've kind of broken it into 3 parts that we'll talk about in detail and come back to this nice color-coded slide so that we're all speaking the same language on any questions. You have at the top section there a 4-bar, which is used for shaping the trajectory of that locking pad and making sure that it's out of the path of the nozzle or such. There is an intermediate parallelizing link, which just needs to be there to constrain the degree of freedom of the system. And then the real meat and bones of the system is the blue and yellow, which is your over center toggle links, which is what creates that vice grip dynamic that rigidly ties the whole thing together when it is in its launch configuration. So to go into these more in detail, again, that orange vertical link, the pad, and the blue, that would be your upper 4-bar. And as with everything else, they connect to that green pedestal in the center, which is effectively your ground link. This was, as I mentioned, designed with the intent of optimizing the geometric engagement you would be getting between the pad and the transition. So you have both a outward and downwards force. It was designed using a principle called instant centers of velocity, where at any point in a linkage trajectory, it behaves as though it is instantaneously a simple pivot, but that pivot point moves around throughout its trajectory. As we developed this, we found that the location of that pivot throughout the motion was close enough to fixed that we can move forward with simplifying this into a design where the orange and the gray would essentially be locked together into a simple pivot. The next part of the linkage is this red link, which serves just to constrain the purple link's motion. It's just kind of how degrees of freedom in linkages work. We're also using it to our advantage in order to actuate this from the outside. As you can see on this prototype here, you can see the linkage from the end, but this isn't going to be accessible assembled into the rocket because there will be a whole sustainer here. So you have to be able to get at it from the side. So all that I'm doing here is I stick a screwdriver and pry down, and that's in between those 2 links there. You get a foothold to move it from the outside. And then, as mentioned, really where the effectiveness of this mechanism comes from is the toggle linkage, where the blue and yellow form a over center. So any force trying to separate this when it's in that over centered position is actually pulling it further into a hard stop. But you have that blue tab at the base of the kick link, which as the piston actuates to move up towards the transition to separate, which you'll see more on the next slide, it catches that tab and unover centers the linkage and allows the whole thing to actuate in one clean motion.
So, excuse me. So what would be catching those tabs is this piston here. Pistons are used quite a bit in various IREC designs, and we have used some form of it also in a few of our designs. Nice thing about pistons is they act as a physical barrier between the sustainer motor and the igniter and any separation charge you would have. So that way you don't mess with the sustainer or excuse me, the sustainer motor in any way. It also applies a uniform force to the bottom of the sustainer. So that way you don't have to deal with pushing the sustainer off at some weird angle due to an uneven force. Does that work? That does. So on this, for this rocket, we have a 6-inch airframe tube with a 4.5-inch inner tube. So that is where the piston would be placed. Through the side of that airframe tube, we have vent holes drilled. So that way, as the piston moves up through the body tube, the gases can vent out, which reduce some of the force behind the piston. So that way it doesn't hit the sustainer motor and potentially damage it. And this design was also made with the intent that if the linkage design ever was deemed unfeasible, we could just fall back to using this piston and shear pins. There's plenty of other designs that use just a piston and shear pins that we could draw from if we needed to. There's just some graphs. I can't actually see them from here, so I'm going to be looking at this mostly. So the top graph is a representation of the difference between locking the linkage, which is denoted by the yellow line, and shear pins. And this is the force actually needed at separation. So for shear pins, the force needed is linear. So the force needed to separate the sustainer from the booster is the same as the force needed to break the shear pins. Whereas with the linkage, the force needed to separate is just the force needed to disengage the pull down force of that kick bar. So when you hit it, all you need, that is the only force you need to separate, is much lower than the force needed to break the shear pins. The bottom graph is an example of, that's my train of thought, sorry. So the bottom graph is a graph. It is a graph. All right, let me look at my notes. Okay. So the bottom graph shows it's a comparison between shear pins and for the linkage. So in the yellow zone below the line, so let's first do this. It's a graph between planned forces along the bottom x-axis and potentially experienced forces on the y-axis. So for along the x-axis, those are forces we designed for. With shear pins, the shear pins are under an elastic strain while we are experiencing forces that we are planned for. However, due to the preload force on the linkage system, we are not actually experiencing any elastic deformation during this period. Now, in the case that for some random reason we experience a uncalculated force due to a crosswind or something else, shear pins go above that line and can fail due to just they are designed to hold until a certain point. With the linkage system, above that line, it begins to experience deformation, but does not fail because of that preload, which negates that force.
For the sustainer ignition system, we looked at various ignition systems before we discovered that per the IREC tag, we have to use the COTS E-match that is provided with the motor. It's going to be connected to the sustainer's avionics bay via an internal pathway. Safety is a major concern that needs to be addressed with the ignition system, as premature ignition of the sustainer motor is an incredibly dangerous failure mode. And the next step is to coordinate with the NP on physical shunting or disconnection system downstream of the altimeter, so that we can make it so there is physically no way for the sustainer motor to ignite until we are ready for it to ignite.
As for our changes for the next iteration over the next coming weeks, we will be moving from a pedestal mounted linkage to a radial mount. The pedestal mount is what's currently in our design. This would require additional piston cutouts for the moving parts and improve overall stability, so we're not having excess moment forces that aren't being counteracted simply. And it also simplifies the piston structure and the sealing of the entire mechanism. Additionally, we'd be simplifying the upper 4-bar into a basic pivot, because the way the linkages are currently designed, they're basically just acting as a simple pivot. So doing that would remove a lot of the excess moving parts in the current design, and also it would allow us to make some more optimal geometry. And then we'd also be modifying the geometry to have a full range of motion by the piston. Other next steps, we're going to finish up these CAD models and do many of the specific calculations to verify the specific size and integrity of all the parts, determine the specific charge and the charge type that we can use to actuate this piston, as well as make sure all of our tolerances are properly aligned, and then better quantify this bending moment to make sure we're actually doing the right thing by moving away from our current structure design. And then, like Raleigh said, work with the NP on integrating the ignition system.
That's the rest.
Questions? We have me working the prototype if anyone wants to see it.
One thing for the locking, there's not really any way to know, like, the charge failed if we release in the locking. Like, theoretically, putting the sustainer fire when it's still locked now.
We would likely have some sort of sensor to determine if they have physically separated, whether that's just a wire running that would break continuity once it's separated. We haven't fully determined what that sensor would be yet, but that we have considered. We would make sure there's some way to verify that there's physical separation before ignition.
For the locking the screwdriver to like get it set and showed, would that be done when vertical, or can you do it horizontal? It's like that might be unsafe. Like, I don't know how we bring that. So
You could do it in any orientation, on the pad, off the pad. I think what's ultimately going to be the driver there is various launches are different in their regulations about igniter installation procedures for multi-stage rockets, because they're kind of this case where you have to do it in an unsafe way, where normally you don't install it until it's all the way vertical on the pad, but there's a certain level of assembly there. But as far as when we lock that would not be a constraint. That can be the last step as far as the mechanism is concerned.
thing that you guys mentioned. Just so you guys know, IRX probably moving forward with doing that instead of shunting, which I also have. So just keep that in mind when you guys start talking with DNB, they should have it be door redundant. It's also just for the safety of people at the pad.
Yep.
Yeah. Then for the 4-bar, you're planning on machining that out of
Likely, yes.
Yeah, so detailed manufacturability plan is still in the works, but I would say combination of a lot of it can be just like laser sun cut sun sheet parts. Some of them inevitably would involve machining, but a lot are basically just a bar with 2 holes in it.
No.
Well, even so, it'll be landing that's right up there. So
Yes.
are you guys looking to figure what they need to have near the front of it for the motoring vents? It'll go like,
Wait, sorry, I didn't hear what you said.
for like the materials you want to use for near where the motor's igniting. Are you still need to look up to that? And not worry about thermal.
Likely not. Unlikely thermal should be a huge concern because of how hard the sustainer is going to be burning. It'd only be exposed to the exhaust for a very small fraction of a second, but we would be doing more like looking into that.
And one area we've been looking at a little bit is the geometry around the tail cone base and how the plume would interact around the lip there, making sure that there's appropriate clearance, that there isn't anything too bad there.
Yeah, I think that was just like a just idea that was thrown out there, but we definitely could just manufacture them like here. They are like there's a good number of parts, but all of them are quite simple. They're
The opposite being, that's a lot of things you're gonna.
Yeah.
A lot of.
Yeah, so that's one thing we mentioned, the tolerance stack up analysis. One thing we'll be doing as a part of that is assessing if this link is plus or minus however many thousandths of an inch, how does that affect your final angular position? And what are your satisfactory actual practical tolerances for each of these parts?
So we're looking at.
yes.
Um,
Really think this is size. I have a few concerns with like the complexity of it. And just in general, like a lot of things have to go right in order to be objective market. So like, I don't think you guys should stop working with it. I think it'd be really cool. It'd be really novel, something to driver. I do think you should continue though working with the piston design. And that should be a very strong, like whatever you do, like shunting and everything should still work.
Yeah, I'm not sure like how clearly this was stated during the presentation, but we just removed the linkage for clarity here. The idea is that the linkage will just be attached in a way that if we're not 100% confident of it, we can just like unscrew it and just have a kind of weird shaped piston.
Because like.
Yes.
Yes. No, like when we did our design matrix, piston and this were very much
They were tied.
two separate items. We had a whole different stage overlap system for that we decided not to move forward with. But what we're saying now is if we fall back to the pure piston, the parts for that are all equivalent to the piston aspect of the linkage, and it can really be a game time decision if it needs to be.
Yeah, at any point up to integration, we can just remove the linkages and just have it be a simple piston system.
So the orientation of every single one of these maybe just the same, so it's good to tell. Is it possible for any of them to move independently of the other languages?
No, it's 1 degree of freedom. You might want to play the animation again, makes it.
Yeah.
Is this the one we don't? No.
Back one, there you go. The animation only played for a little bit.
Wait, sorry, it was working differently when we did our practice run. Okay.
There we go. Yeah, that's what I wanted to see.
Yeah. So pushing on that blue tab, that forces the entire motion. There's no separate anything.
Correct.
But also for slide 14. We were talking about some disadvantages to shear pins versus the linkage system. But I'm curious because we're expecting a little bit higher wind conditions or higher loads in the rocket with more shear pins. And also related to that, you mentioned that in the case of unprecedented high loads, that it would deform. And I'm curious if we have any idea, if we've done any sort of analysis on the deformation that might occur and how it might affect this.
Okay.
Would it still function?
So to explain the difference going on there a little bit, imagine the linkage system as it's pulling down on a spring, which just represents elasticity in the various parts. So you have this normal force pulling down on the transition. For any motion of the transition to occur, even just tiny angular shifts due to bending moment, the first thing that has to happen is for that axial preload to be overcome. Whereas with a shear pin, because there isn't the axial preload, any amount of force, even if it's below your designed force, it is imparting elastic deformation and giving you small bending moment within the joint.
Specifically, you mentioned deformation in the linkage being possible, and I'm assuming that's not something we're like thinking is likely because obviously factor of safety, et cetera. But I am curious if that does occur, as you mentioned, what sort of, where is it occurring and does the system still work? Because if it deforms instead of breaks, that's fine, but if it deforms and doesn't work, then it's still not.
Yeah, I would expect the deformation pathway would be essentially along that vertical tension bar. So essentially straight up and down.
Not. And then also on your point of to resist higher load, we can just add more shear pins. One of the strengths of this design is that whereas shear pins, the retention force it can provide also has to be overcome by that much separation force. This one can provide a lot more retention force than the force required to separate it.
And also I'll add that one of the concerns we had, and we definitely like to quantify this more as some of the other teams lock in some of their mass estimates. But with the two-stage design, the bending moment at this joint is going to be very high because you have the entire mass of the sustainer, including motor and also aerodynamic surfaces above the joint, which is not something that the team has done before. So the bending forces are non-trivial, and we wanted to explore designs that would really squash them down and see if they were viable. Yeah, so again, we will definitely be pursuing that, especially as we get better mass estimates of everything. It's just our first order sense was big.
Yes.
The sustainer still be used in or now?
Yes.
Okay. That's fine.
Yeah, that was one of our, I forgot to list it on the slide, but that was one of our design requirements
Yeah,
going in.
with all of our designs, the sustainer was completely independent.
Yes.
That would be order of events. That would be like, we have first stage burnout, you get like a coast and then separation, coast ignition, something like that. Do we do that?
Yeah, that would be.
Yeah, there'd likely be a very brief coast, like likely under a second, and then the charge fires, which actuates the linkage, and then in that same motion forces the separation of the sustainer, which then ignites almost immediately after. Yes.
No. Possible if there is wind. So like if we're not, if there's any angle of attack, is it possible that the pieces that are grabbing onto the tow could impart movement? Like where that wouldn't be imparted if they weren't there?
I don't think so, as it would be interfacing with the rest of the sustainer, even going to after those would fully be clear to the tail cone. However,
I would expect the outer cone constraining that is just going to be orders of magnitude more rigid than than lengths. So, speed.
We're gonna have to cut the questions up there. Any other questions can be put in the formats in general. Okay, thank you, guys.
Oh, there you go. Okay, this one.
Jazz, can I have this up to you? Can I have this up to you? I don't want to know, please say no.
Of course.
Move to the table.
Okay, now let's just move forward. Everyone take one step forward, like toward the middle. There we go.
Okay.
What's the last thing you said?
Yeah.
For money times, you can just take the.
Yeah, he's no GPS and Actuation. Interjecting with the design.
You guys are good to start whenever.
For electronics design. Just to start with an overview. It kind of all spreads out from the microcontroller. So at the top, we have the power. So power comes in from the battery. And then we go into a 5-volt regulator, 3, and then there's a 1.8 LDO for a special sensor. Things that interface with it, we have the GPS that directly interfaces with it. We're going to have almost a shell type concept on top of this board, since we're shrinking it down to around 50 by 50 millimeter square, opposed to last year, which was a 69 by 69, but we're able to reduce the size because we're taking the radio module off and also switching out the radio modules. We have sensors that it integrates to, and then just some supporting hardware for the microcontroller, including the flash, the SD card, and 2 crystals that it needs to support itself. Next, this is the microcontroller. It's not done because we still have a few more things to interface with it. We're still using the same STM microcontroller that we used last year. We're using I2C currently to interface with the sensors. We might switch that to SPI. That was a recommendation that we got after having it reviewed from someone like one of the electrical engineers at the Naval Energy Warfare Center that I reached out to. There's going to be some general purpose pins once we figure out general layout where we can fit them in. It's going to be a very tight fit. And then we have sensor interrupts, the flash, like I said before, and UART to the radio. This year we took off the USB hub. We're just going to go right to the microcontroller, and that can disperse to downstream ports. Power, like I said before, power goes right from the battery to the first regulator that we have, bring down to 5 volts. We integrated a bunch of different jumpers, if you will, so we can basically separate off power in different segments for a better bring up of the whole system in and of itself. So there's cutoffs right from when the battery comes in up until right in front of the first regulator, right after that regulator. So we can basically probe as we go to make sure that nothing blows up in the burn. You're totally fine. And then also another recommendation that we got was for the LEDs to be directly integrated into these ICs before we had a separate line going to the microcontroller, which then would pass through to a LED. But now that it's directly integrated if there's like power for just the regulator, and so let's say not the rest of the board, that LED will actually show in true value if that specific IC is working. Power continued. This is the other regulator that I talked about, which basically just steps it down to 1.8 volts for the other sensor. And then there's a voltage mux on there, which just picks which 5 volts it wants to use. So from the battery, or now the IC that it just converted down to, or once we do the USB, which we'll talk about on the slide. So again, we just used USB-C like last year, which was an upgrade from micro USB, I think. Again, like this just goes right to the microcontroller, opposed to going to a USB hub. We're using the same, the SD card is going to be based on placement. If I can get it towards an edge, it'll just be like a push out one. But right now, as of last year, because it had to be like centered on the board, we use like a hinge type, because like there would have been like obstructing components in the way of it ejecting it. Onto the sensors. This is a new sensor. Screwdriver. This is a new sensor. This is our high G sensor. It can go up into 200 Gs with 100 or 10,000 G shock survival. Hopefully, we don't have to use that. And then this is just an accelerometer, so then we can do EKF. Those are the parameters at the bottom. This is the low G one that we'll be using. The LSM. Again, the parameters are there. And this one's also mainly just for the accelerometer on it. After that, we're basically up. We're actually equal to the amount of sensors that we used last year, because we removed the temperature sensor, which we can now just integrate directly into the pressure sensor. This is an IMU, so this is where we're going to get our magnetometer values from gyroscope. Those are the tolerances for that. This is the same one that we used last year. And then the pressure sensor, which is also the same as last year. After PDR, we switched it to an older version, actually, because their newer version didn't work properly. So this is the one that we still ended up using as the final one last year. Radio.
So for radio, this year we're using a new radio. It's going to be the eByte LoRa module, and it works at around 220 136 megahertz, and it's going to take an antenna input from an SMA connector, and which is going to feed into the radio, and then it communicates over UART. And then we chose this radio so we could have a longer range compared to last year.
Like Chaz alluded to earlier, the radio board is not on the Mars board this year. Instead, it is being raised up above it, so that we can get the Mars board into a smaller footprint. In the bottom right, you can see the 3D printed stands to do so. The red and light blue are 3D printed out of PETG. The gray is the size of the radio module with respect to what is green, the Mars board, the new Mars board at 55 millimeters squared, or per side, not squared. Anyway, sorry. It will be a bit of a tight fit, but this will be able to include the connection to the antenna as well as the matching networks and the JST connectors that will take all of the data down into the Mars board. The height is about 1.3 inches, giving ample space for the XT60 connectors for power, although we will likely not put it over that. I wanted to give it a liberal amount of room. And it would be attached with M3 thumb screws for ease of disassembly and assembly should the inevitable happen where we need to access what's under it.
Yeah, to that point, we would be either integrating this with a ribbon cable to it with a connector on top, and then it's just like the supporting hardware on the sides, or we could also do almost like a JST, like how we did the not Polaris, the three stack from like 2 years ago, where it's just like a JST to another pin header at the top. So we're still looking into different options with mounting and trying not to obstruct different things, because like the voltage regulation path generates a lot of heat, so we don't want to be above that really. Then we also need to clear the SMA that goes to the GPS, which is next.
For the GPS, we're also using a new IC. This time it's the Tessio Liv3F, and we chose this to allow for access to raw sensor readings, so that way we could improve our GNS algorithms, mainly navigation. And the way this GPS gets signaled, so we have an off-board patch antenna, passive patch antenna. This goes to an SMA, and that signal will go to an RF amplifier, followed by a SAW bandpass filter to get rid of any noise. And then the GPS will communicate to the microcontroller over I2C. And then the RF amplifier and the SAW filter are based off of the GPS hardware manual.
So still to be done. Like I said, based on PCB size constraints, we'll do the general purpose pins like last year. We ended up getting like probably like 10, let's say. Some of them were used, some of them weren't. We also need to talk about how we're going to do the boot pins and the resets, because last year's way that we did it took up a lot of area. So we're looking into different ways of constraining that with like reliability in mind, because we don't want to just put buttons on there that could just be pressed and reset our microcontroller or XP or whatever mid-flight. So that's a consideration. We're also looking for best ways to connect the camera. And we also have MOSFETs, which are actually coming up. And then we also just have to meet with Payload to see what they need in regards to amount of pins available. Ideally, it's less than last year, and last year's where we got enough on there. Power system calculation, we haven't started because we're still selecting.
My slide is gone.
We had a MOSFET slide, which apparently isn't there, so you can just freeball, I guess.
Yeah.
We haven't started. We're waiting on if we change the servo for the air brakes. We're waiting on if we change any sensors possibly, but we'll get that up to date.
Speaking of up to date, I have some things to say about MOSFETs very briefly, which is that kind of last minute. We have some MOSFETs to power the camera feed. What? Oh, okay. Hi. We have some MOSFETs to power the camera feed or whatever else is needed through GPIOs of the microcontroller, just so that we can control things low side using that lower power signal. They're, oh gosh, I don't remember the exact number, but they can take 3 amps, 3.6 amps. They can be turned on and off with a signal voltage of like 3.3 or 5, the gate source being 2.6 volts. So which can be produced by the microcontroller. Yeah, so we can use that to power various things low side for whatever's needed.
So,
yeah.
No questions, great.
Oh, yeah.
Any questions?
I have one probably doesn't matter. LEDs, power LEDs now directly from the chip, which is probably good.
Yeah, they have a designated pin, the P-good pin.
Yeah, I don't think P-good is supposed to source. So like before we're just going to the microcontroller, that's fine. I think you should do LEDs directly off of the VCC line. Because like if the power is good, you'll have power.
Okay, well, I'll relook at the schematic. I haven't looked at it since last year, but I think this is like I think the point of that pin is for this purpose,
Okay.
possibly, so.
But I assumed it was like logic and you could do things on it, but the LED will take actual current and thus should
Yeah.
go through it. It's like, just to make sure. And probably don't, like there's maybe a chance that you could power an LED and still have you could do well, but I don't think we need to worry with that case.
Okay.
And then the other thing was, so we're getting to the USB output, the thing of mine.
Yeah, very.
So the only downstream USB device right now is the GPS module.
The GPS uses I2C.
Right. But last time we also had it connected to the USB, I think, because we were like,
Yeah,
the USB and the XP.
and then we also had UARTs, which went to GPS and the XP, yeah.
Yes. Yeah, so do we still have that this year? Have those been rerouted to microcontroller pins? I guess there's no.
Yeah, so the USB connector goes directly to the microcontroller,
Yeah.
which should be able to support the only downstream peripheral being the new radio module. I need to figure out where I want to put the UART chip because like that means that I now have to put like a more pin connector to go up to the shell.
Don't have any actual USB. It's just UART score.
Correct, yeah.
Because then we can make sure that all the pins, correct?
Mhm.
Both the host and
Yeah, and then ideally the USB-C, if properly, also configures the microcontroller.
yeah, that was.
Yeah, and then there's also the initialization pins, which was on that original diagram because the microcontroller doesn't know what to do, what to read from at the beginning. So you just need dedicated pins at the beginning to initialize it and be like, hey, these pins are this. Hi.
Yeah, two quick things. One, we also have speakers to the board, so which on screen switch it's on. I know like we have like you can track the radio, but like just that much effort to put the speaker on there. You can say no.
No. I have to think about it. I'd say if it can go on the shell, that would be more ideal. That just means wires to go up there, but the speaker, good idea, but it does take up a decent amount of area.
Okay. Yeah, I just,
But if I can fit it at the end, sure.
yeah, 'cause one of the things, at least on the time last year that we had issues with, radio was like buggy.
Mhm.
Like we had issues knowing if the intelligence was strong, which just had more delays, the already delayed volume and stuff, so. Okay, like we just a good way to know, like, I actually got this switch. Even if it's like, I guess the light look like it's super bright up, but just something.
We can take that into consideration.
Then
28.
two questions. One is schoolhouse, but my quick one is like, are we sure this is gonna be like stable?
Yeah, like in terms of like during flight,
Yeah,
I mean, we haven't run tests on it, but we can do a good old shake test. But it has four screw holes. It's only an inch high. It'll be fine.
and then on that site, what was the reason for that?
So each XT60 connector is roughly half an inch tall. So since it's a male to female, it's about an inch tall, and then I gave it about 1.5 extra times extra to make sure that there's clearance. So that's the tallest thing on the board. We likely won't mount it over that area, but I wanted to be safe.
Like the back site,
It's like, yeah,
Definitely short. Ideally short. Because even the XT connection can, if we even go with that connector type,
yes,
can also be a 90-degree angle.
yes.
Coming from the side, but like last year it was more ideal if it was coming on straight on.
Yeah, so once we know where it's mounted over the board, we can measure to that instead.
Okay, yeah, definitely, like, if you get a higher, I think, like. But the mechanism, especially if we're trying to do like the larger array, it's gonna be nice to know, like, what's our max height.
Yeah.
Oh, 53, yeah, sorry, I got confused.
Yeah.
So we aren't doing airports.
Just confirming, would the payload be able to have ISO and SDI and I2C bus?
Yeah, the microcontroller has many pins, many pins. And I got rid of a decent amount with disconnecting things that are no longer on the board.
I know we used it last year, this is flight 20. Like, I know we've used it and it works. I'm just curious, is there any like specific reason for this microcontroller? Like, are there other options? Or is it more just it works? There's no reason.
It works. It was selected by the team last year. I didn't put any like consideration into like switching it really. And it supplies the needs that we need. And we were like, I wouldn't say that we were like maxed out almost at the end of last year. But we were getting close to it despite there being so many pins.
On slide 24, maybe this was a miscommunication by me.
Oh no. What?
So with this, you have 3 IMUs. 2 IMUs, and then this accelerometer.
Or is it two accelerometers? and-
Yeah, so it's IMU accelerometer, so.
Well, the other one is also a 90.
This one?
That's the child.
Hmm. Yeah,
Yeah. What's the difference?
the G rating, so then we can do the EKF. Because like off the pad, it'll be higher than
You just need 200.
this one's rated for.
Oh, I guess, I mean, the IG, so
Two IMUs, and there's IMUs on that it's the gyro and Excel.
well, I just, the high G accelerometer, like ideally, we're not saying 200 G.
Oh, unless already goes.
Yeah.
That's the.
Oh, so you already did the DDC, it can't hurt. If we hit around really fast, like we can record it really.
I was gonna say, it's happened before.
It's fine.
17 Gs 2 years ago.
Oh,
Anyway, okay, that's.
we can exceed it.
that's fine. I mean, if it's already on the board, it's fine.
Look at the shock wow.
Well, but it can't read, it can survive, it can't read up to it.
Okay, I have a question.
Yeah.
The SD card, just out of curiosity, have we ever had an issue with the premature like SD card ejection?
No. Because it's like, it latches down.
It does, okay,
And
I
the-
wasn't sure if that was like what that kind of, okay.
I'm only EC, but like, I feel like the force wouldn't. that way.
We haven't had an issue in the past, and like we've come in ballistic, I'm sure.
Also a SD card thing. The STM chips, or at least this one, has a like dedicated SD peripheral. And we can use SPI, which allows 4 times the data in scroll lines.
Ooh,
Look it up to that.
Sure.
Like, have the bits that are, because I believe they usually do it so it overlaps with the SPI bits. So if we want to use SPI, if we don't get this thing working, we still can. But if you look up the remaining data codes to wherever the video is, the SD.
did we look at this last year?
Well, I think we did, and I just really know that what it was last year.
Okay.
I think we should.
It sounds familiar. I don't know why, but yeah. I'll switch me.
Like,
I think that's why we didn't change it.
Well, is there a library? I only think it's.
I found
Have a
something
library.
buckets. But there's at least.
Okay, this is definitely gonna be a strong point.
Okay.
Slide 21. Why do we need like such a big output? Do you think about 1 volt? It is, we do have stuff for that, what? I just don't like, we're actually, like, this stuff, do we have things that are going down to 1 volt?
Yeah. We
Oh,
like to go to the next
So
one.
we're, yeah, 1.8.
Okay.
But that's an LD.
Well, it takes a large input sweep, so it can go from like 6 to 36, whatever it said. But then we go from 5, and then I think that's a lie where I said 5 volts to 1.8, because it goes from 3.3 to 1.8, because the point of an LDO is just like close enough voltage. Fancy EC shit.
Okay.
But yes, we need it because one of the sensors needs 1.8.
Okay.
And also that means that it needs its data line to be 1.8. So then we have a whole nother annoying IC to bring that up to the same voltage as all the other I2C lines.
Okay, I just.
I'm curious. Okay, maybe go back.
Oh, like the USB and.
Yeah, but why do we
Okay.
need it to come from different places?
So just in case, like, say the board's powered with a battery, and then we also power it with a computer. And because we want to like program something, it'll pick whichever like voltage is better and more reliable. I think that we auto set it to take the voltage from the computer. So then we don't deplete the battery for no reason.
So it doesn't have any effect during flight,
No.
just for when you're.
Yes, it's only like lab setup wise, if you want to like pick and choose.
Yeah, like for air brakes, you can put the batteries plugged in. Then to test the air brakes, ideally you plug into a computer. That's, you don't.
So it's mainly just for testing and then like like we just say like batteries weren't used and we just use the voltage has to come from the computer already. And then you also have the case where the voltage is coming from the battery. So then in the case that both of them are there, it doesn't know what to do. Do you need this first step to be like, hey, which one?
I also do have a question then, which is if it's usually drawing from the computer when the computer is an available option, the computer is supposed to be the other regular, then that seems like we're testing in optimal scenarios as opposed to, let's just say,
Because it pulls from after the regulator. Because the voltage say comes in at 20 volts. The regulator brings it to 5, and then the boxes afterwards do like, hey, we want the battery 5 volts, or this now regulator that passes through 5 volts, or do we want the computer 5 volts?
You said, I don't know if it's actually how it's set up. I think last year it was the battery was the default equipment. Because shouldn't it be in case if we're testing the battery, probably it's something that's needs a lot of batteries and then we should not the USB.
Yeah, I do.
So the battery, if both the plug-in, it should be a battery, and the USB should not be powered, it should just be within.
Yes, it was just weird because I think that the USB hub, don't quote me, but it was drawing based on the USB voltage, not the regulator's voltage, so it wouldn't be the pain, but
So for I just wanted to make sure it's sort of on the same page. The issues that got higher last year, that's the too small sort of lines that like the training for that sort of solid everything, like we know which ones are too small.
that was with basically with the payload change, so nothing, and nothing.
Okay.
Regardless to treat, but all of them.
So with that, when do you need these payload?
Like we were really pushing it last year.
For the GPS, maybe I misread the documentation. I thought the GPS had the amplifier and the software, or does it definitely? I could be wrong.
There was an additional hardware manual that was like in the appendix, and then that asked for like an RF amplifier. Yeah.
Okay. Yeah, I mean, that's what
I had the same question.
Thomas has the avion slides.
Oh, the avion.
Yeah. Off the board, it takes a picture first.
Oh.
Which parachute ones do you want to do?
He's helpful. Yeah, we need some.
Okay, just let me know. I'm ready to do all of the parachute. I'm ready. Just let me know when it's my time.
What else?
All right, so we're the two-stage rocket recovery team. Just a quick timeline. A term, then it was all research and preliminary CAD and calculations. This term after PDR, then we're gonna do our wiring diagrams, revise the CAD based on any decisions that are made here, and then I will do parachute folding and hopefully print up a prototype sled for CDR. So quick overview, our sustainer will have dual end, dual deploy. The drogue is 36-inch diameter and it will deploy at apogee. The main is 96-inch diameter and it will deploy near 1,000 feet. The booster is only single end, single deploy, and that will have a 24-inch diameter parachute that deploys near 3,200 feet. We will be using solely black powder charges for separation. This is a quick, it's a little blurry because there's a lot in it, but it's basically a flight path diagram. Yeah, Matt, it's a little blurry, but it's got the time, the altitude, and the velocity that we're moving at each of the major stages. So after burnout, then there's the booster cruise, separation, sustainer cruise, booster parachute deploy, we hit apogee, drogue deploy, and then main deploy and our landings. So that's for reference. If at any point later, people need to go back and see that.
Okay, so these are the parachute requirements that are set. The requirements on the left and then our specs are on the right. So the drogue has to deploy at or near apogee, and a descent rate has a pretty wide range of 65 to 131 feet per second. And the main needs to deploy at or below 1,500 feet, which John just mentioned last slide will be good for that. And that descent rate has to be under 36 feet per second at landing. So our current specs, based on that, we have our drogue deploying at apogee with a descent rate of 65.42 feet per second. And the main deploys under 1,000 feet at about 964 feet with a descent rate of 16.21 feet per second. And then also the booster will be deploying at apogee, what it's supposed to. So this is our main parachute. The supplier Fruity Chutes only had one option for the main parachute. So we got the toroidal parachute. And again, it gets us that descent rate that is within our range underneath 36 feet per second. We have the calculated opening force, opening time, and then the packing dimensions right there, which is why we're spending so much time folding parachutes at our meetings. Wait, does this one also need? Okay, this is our drogue parachute. This one has two options, and it has the 36-inch toroidal or the elliptical. As you can see, the toroidal one, the descent rate's a bit too slow for the requirements. That has to be within 65 feet per second. So we went with the elliptical shape, and also Matt will be happy because it's cheaper as well. So there's that benefit.
So Fruity Chutes only has the one 24-inch diameter parachute, which is elliptical. So that's what we'll be using for our booster parachute. And that will be coming down with a descent rate of a little under 80 feet per second, which is fine because the booster, since we're not actually at IREC, then it doesn't strictly need to follow the IREC rules. But if we do a booster in future years, then we'll need to look more closely at the descent rate.
These are the avionics requirements that we have to follow. So initially, it has to be completely independent and redundant recovery systems. At least one of these systems has to be a COTS flight computer. Ours are actually both because we don't make our own flight computers, we buy them. The batteries changed this year, so we're going to have to find some new batteries, and that's something we're looking to research and decide on this term or this upcoming term. And then also the last requirement, which basically is no active explosives until you're ready to launch. So we have that covered with switch bands and appropriate CAD models to make that easy to activate on the launch pad.
Okay, so the primary altimeter is going to be a Blue Raven, and we've used this before. It's another company, Featherweight Altimeters. It's screw mounted, has multiple sensors, an accelerometer, barometer, and gyroscope. It can be mounted in any orientation. Has a max altitude of around 45,000 feet, which is excellent because our apogee is around 5,700 feet. It has 4 channels, dual deploy, main and drogue. Has Bluetooth and micro USB, and batteries. Has a wide range, like for compatibility, from single lead polycell to a 16-volt pack. Yeah. For a secondary altimeter, it's an RRC3 plus. It's under Missile Works. It's under a different company to prevent any manufacturer issues. It's also screw mounted. It only has one sensor, and that would be a barometer. Its max altitude is much greater than our primary altimeter. It has 100,000 feet, which is then again much greater than our apogee of 5,700 feet. Has 3 channels to deploy as well. Bluetooth and micro USB as well. And the batteries, it can be a 9-volt or a 3.7 to with a range of 3.7 to 10 volt. Yeah.
So this is the sustainer bay for our sled system. So so this one is dual end, dual deploy. So there'll be a parachute attachments on both ends. It's 10.5 inches in length. We'll have 1/4 inch threaded through rods, and this will house our altimeters, Blue Raven and RC3 Plus, and the bulkhead is made out of G10 fiberglass, which has and the diameter specifications. The outer diameter is 4.85 inches, and the inner diameter is 4.88 outer diameter and 4.85 inner diameter. And then for the box inside, there's also an image that will show you which different parts we're referring to. So the Blue Ravens right there, battery board. There's space for a telecommunication GPS system and for the battery cell as well. And there's also the 8-gram charge and the RC3 Plus altimeter, which is on the back. As for the recovery sled, this one's single end deploy, so it's just going to be one parachute attachment. It's going to be 5.9 inches in length with a diameter bulkhead of 5.88 inches to fit inside the cupola. It will be the threaded through rods are also 1/4 inch. We'll also house the relevant altimeters, and it's also made of G10 fiberglass. Moving forward, we'll work with structures on mounting. So should be a slide that shows the different components. So you have the 8-gram charge well, the different altimeters, space for the battery board, and the upper bulkhead. There's also the backside. There's also space for tel GPS and the lithium-ion cell battery center.
So moving forward, then we'll be calculating line lengths and drawing our line diagrams, as well as making our wiring diagrams for both the booster and sustainers. We'll be determining which sustainer sled to use. Taha kind of glanced past it, but there's right now a sheet design, which is basically just a thin 3D printed board. And then because that could have trouble being printed, then we have the traditional box, which is, it's a wider print, so it's easier for the 3D printers to make. So depending on which way we end up going based off feedback tonight, then we'll be moving forward with that design. We'll be adding a camera based on what our rocket lead gives us for how many cameras and where they need to go. And then, as was mentioned previously, we'll be working with structures because for the booster, then the upper bulkhead will be mounted with the booster coupling. So we need to work with them to find out where we need to put those mounting holes. Any questions? Yes.
I have on the recovery thing. Are you considering provisions for, in addition to the recovery separation charge, of the other sides of the bulkhead having the charge for stage separation?
What do you mean considering provisions for, like, in case the separation fails, having something to force a separation or to protect it?
To wait for the whole thing?
All right. Yeah, we haven't discussed with the separation team yet. So we were just for recovery separation that only one side needs the charge. So I'll have to talk with Riley to find out what size charge he needs and where he needs that to be.
Yeah.
But thank you for pointing that out.
And my second bigger concern is the decision to go above the IREC descent rate by a factor of 2 or more on the booster seems concerning to me, and that it's well into the territory where you would expect to see damage or safety concerns on the ground from the falling booster.
So right now, then we don't believe that there should be damage, but if we were to put a larger parachute in there, then well, we'd either have to do a dual deploy to have a main and a drogue, which is what you'd have to do if we were at IREC for this because it goes above 1,500 feet. Or we'd have to just put in the one massive parachute that would drift. So the decision was made for those reasons that we're just going to have the one parachute, and because it's not out of competition, then it's not as critical. But that would definitely, should it go to the point where we're out of competition, then it would need to be done. For that, we have the correct steps.
I think it'll be fine because there's a few.
Yeah, that's just in the territory where I expect you would run into like.
I agree. I just wanted to go down the path so that I didn't want to do school one.
I was just gonna make a comment on this, that same thing, I think it's fine if that's the decision that's being made, but make sure that you're communicating that number of force. Well, I don't know if you're calculating that or infrastructure is calculating that, but someone needs to calculate the anticipated force upon landing as we're moving a little quicker. Make sure that specifically I'm thinking field code is.
The composites are.
Yeah.
All right.
You go to slide. Okay, so, yeah, that one. What are the spots? For this one, the GPS antenna.
I know it won't fit on the booster, so I don't know if it can wrap around as long as it's still pointing up, or if it has to be.
At some point, talk to Nick about it, what were you?
No.
But, I think, like, we talked about shortening the wire last year, and like theoretically it should be fine, it just makes it less good. Yeah.
So that is a concern that was
Yeah,
identified, but
I also don't know if we need it in the booster, I have to look the requirements again for that, because they're very ambiguous about where you need tracking.
for IREC, then it's in every
It
separate
is.
recoverable, so the booster would need it. Obviously, we're not at IREC
Yeah.
with this, but in future years, it would need it.
Okay, because because we're having so much. We'll talk about it. Yeah, the spot tracker.
With the spot tracker, yeah, if it's just the one factor.
Yeah, we have, like, the fact, like last year, the one of the intelligent guesses.
But you can also,
We can.
like, well, yeah, the wire doesn't have to be like a perfectly straight line. I don't know, like, what is the structure? If the structure is 3 rigid.
Yeah.
So like you could just have like a hole and have the wire feed inside the structure or something.
Alright.
Because it won't, it's not.
Does it just have to be pointing down or up? Or does it not matter as long as it's in there?
Not really.
All right.
As long as the end isn't like, as long as one end isn't pointed like directly at the antenna, like it's not.
Okay.
So the detail you also recommend mounting batteries with terminals like that horizontally. Is there a reason it's mounted vertically?
No, that was just a rough, like, for placement, but it can be rearranged.
And more of a comment for the box design on 49. Is that your comment?
Yeah.
Could you print or what's the longer one?
Do the center.
Oh, that one. Oh, okay.
Yeah, you can't see it like this, but this one, then it goes, there's a length and a depth to it. It's just the view of it was to get the components, but it does have depth in it.
Was this the one you were concerned about 3D printing?
No, that was the one before it, the sled, because that is literally just the spots for the through holes and then. Yeah, that's just the spots for the through holes and then a flat sheet.
I was wondering if for this one, you could print it in sections, that just.
That's an option. Yeah, so we're looking for feedback from the club on which one we should go forward with. That way we can eliminate one and progress.
Not using all the space that's available. Why do we need to have that much space available for not using it? Can we just print a more reasonably sized section and fit everything a little closer together? And then just, and you already have threaded rods. So if there's just nothing in between the threaded rods, it's pretty smooth.
We can just print like the end sections as long as it's the 11 inches or because it needs a caliper each side and then the band. And just have empty space, that way we're not wasting filament, as long as we keep it at that 11 inches.
Same, maybe question. That 10.5 inch length is fixed, right?
Yeah, but you have to have a caliper. Yeah, you have a caliper inside each one.
Right. Okay, I was thinking, like, you don't need that space, but if you.
You need for the length itself, it's, yeah. That's
Okay.
Okay.
Yeah, I know.
Yes.
I've actually playing.
So far as we know, I mean, okay, what we've written on, I just like, we just like, consider the atoms testing. It's slides.
Yeah, so say, isn't the first one?
Or actually, I just go, yeah, it's actually, yes, like, and then there, it's like, I think we go. Yeah, I'd like to pass. If during it's the same time, it's that I'm not sure that that's in there. So it needs to be. Separate.
No, so, because there's not, like, something, everything happens like.
It doesn't take us to be very. But it also might be say, oh, actually, this is, that sounds like nothing, but also whatever. It's a.
I have first. What is actually station is yes. Oh, station.
Oh, yeah. Yeah, I guess we say what we have. Yeah, that's it. That's the thing. That's what. Detail things on those that may, but I think they're gonna. Oh, really? It's that. Oh, okay. You've got. We've been like an hour.
Yeah.
Already mad.
It's been hard working.
That's it.
He wasn't paying attention. That was still like, it's.
What you think? It's not to do is just It's in the trade-off with drift versus hitting the ground. It's always gonna hit the ground, it's not necessarily always gonna drift. So, yeah, that's a good territory. It's like, if it hits someone's car, it goes through the cautionary.
So people already submitted. They already have a score. 2 days in. They already have a score. Damn, granted, they only got 2 final. Oh, this is the 14 months. That's one page I had to put in this. It's a concept of which it's not. Today's guy. Yeah. I did, there were, when I looked at the wedding, there was like here. Our next score is 5 minutes. What is the maximum score? There you go. You're one, I think 5 minutes. For the time. Wait, it's only 1 5. So look, that's almost. I'm looking at the whole. This is a dynamics. Are you can get into the list like it's the entire. Yeah, but did you read the problem statement? I'm not. Part of the. Yes. Actually, what he's doing. The entire point is that we're. So I know. Well, he does write numbers for all his chaos. Like, when I hear it's like 9 different. But I think that's what we're doing. So it's kind of like, we can't just send it. That's part of the sport. It's like. I mean, I got to get I'm sure it's like you just keep it because it's score based, so it's like you get your score higher, spend like. Like, is it just English? So it's like they're on the others. Like, I know the film. That's a computer. It's like real similar to any we supposed to say except and like the points you get there. We don't know. I guess they something. What's interesting? I want to actually try this. This is like the human. Yeah, let's see what it is. Yeah, maybe use that diagram. Because you're
Charges and stuff. This is. Sure.
Well, we're coming in.
Actually, there's, we don't want that.
Yeah, I mean, it's.
Big difference, there can be, especially.
But like the planet accident, it's really. It's like one Sure, it's not.
Yeah, that.
I tried to make it up. Oh. How much did you do? A lot of things that also. I said that, yeah. That's a good.
Did they simulate?
I'm assuming they have some sort of control.
There is somebody for this. It is passion contract.
As the guy tries to. Yeah, no, right, it says 16 patch.
Yes.
It makes it, yeah, it's otherwise probably. What you told them? Oh, that's on this one.
Yes.
What you do, what you do.
Oh my gosh, what's going on?
Isn't it? That's it. No, doing the thing. I'm getting up. I heard it wait.
Time we can wait here.
What percentage of the slides?
I didn't put any code, which is why this is really short. So you should let me put code because it's gonna be like 10 minutes at most.
This is like a direction.
Yes, okay, you're all in Russ. So, hello, we are Flight Software. This is a somewhat new sub-team. It's really just a combination of Rocket Software and Payload Software from previous years, except some of the Payload sub-teams will also be writing some code. So we're really just like coordinating all of that and then writing the code for the SRAD avionics on all of the various rocket projects that we have this year. So we have a timeline of stuff that has already happened and has come. And then we'll go over like the two main systems that our code is made up of, which is the state machine to track the stages of flight for the rocket and for the payload mission, and then sensor management and logging and playback and various things there. And then we have what we're doing to achieve reliability and testing our systems as well as possible. And then we'll talk a little bit about integration we either need to do or have done with other subteams. This is sort of an incomplete list, but it's okay. All right, so timeline. In A term, we did an initial design, not really code, a little bit of code, just like thoughts on what we want to do for all the systems. We set up GitHub repos. This year, we have some code to work off of from last year because it's the same hardware. So some of that's being reused, some of it's being rewritten, and that's basically what we decided in A term. So this term, we will then do an initial implementation of those designs with at least enough of it running by November 15th to get data from that launch. There probably won't be radio communications then because that involves new hardware that's not done yet and some integration with ground station. So this will just be purely logged data. And then also in B term, we'll set up unit and integration testing for our code so that when we make changes in the future, we know it still works. And then C term, we will finish the things that we're missing in B term, such as the radio communication stuff, the payload mission, whatever else needs to get done that is sort of like part of the project, but not the base code. And as much testing as possible in C term. And then D term just says more testing. That's not true. We'll definitely be writing more code because it always happens. But ideally, just testing and making sure everything's good. So on to the state machine.
Okay, so the state machine in terms of functionality is going to be very similar to last year. The main difference is we are trying to move away from a more object-oriented approach to something that will be easier to understand and maintain. As for how it works, each state will represent a discrete stage of the flight. It'll take in data from the sensors and then either produce the next state if a transition is triggered, or it will return the same state if we're continuing the same stage of flight. Each state is tries to be as modular as possible, so they are defined in their own files to make it as easy as possible to maintain and modify or create new states.
So the state diagram is basically the same as it was last year, and it works for both the 30K rocket and the one we're going to be launching on November 15th. And it has arrows to like the next state as well as to itself, as well as abort.
For the two-stage state diagram, this one is similar, but also a bit longer. So from the start, you have some initialization steps. Then you go through all the states with state transitions, which we don't exactly know what will look like right now. And we are also a bit unsure about how the stage separation state will look like and like around it, what will happen. We think there will be a coast stage before the separation. Then at the separation stage, we will have to do a bunch of checks to make sure separation happened correctly. From there, either do a stage 2 boost stage or go into some failed separation state. We don't know yet. From there, yeah, go through all the states. And for this state diagram, this is from the perspective of the flight computer on the second stage. And yeah, whatever we decide, because of the system we're using, it will be easy to implement. I don't know, either jumping over the ignition state for the second stage or going into like some alternative path. That should work anyway.
So sensors are going to be basically the same this year as they were last year. We do want to change, however, data access because it was a lot more complicated than it should have been. Maybe it is how it should be. I don't know. We're going to look into it. It was hard to use, so we're going to change that. We're keeping the idea of abstracting out hardware information about sensors. So actually using them, you don't need to know about it. You just said you have it. So yeah, so if like we change sensors as well, we don't need to change code that much. Yeah, so this is how interactions will be with sensors. So getting data, you only go with sensor manager. You don't actually touch the sensors themselves. So that polling rates and all that is kept the way it should be. Yeah.
And for reliability and testing, here's what we're doing this year. So first thing, as mentioned before, we're moving away from an object-oriented approach towards a simpler solution that'll be easier to maintain, test, and develop. We also plan to do a lot of testing. The main three ways are to use recorded data and play it back to the state machine to check the state transitions and basically everything in the states is working. We also, before that, we'll be doing platforming unit testing on each state, basically just designing the test conditions and checking that everything works on the embedded device. And then we also plan to use a Raspberry Pi to kind of interact with the hardware and test it that way to be testing on the basically the flight computer that'll be flying, testing as much as we can to ensure the highest reliability.
So now, like I said, a kind of non-exhaustive list of integration things. Some of this, well, actually, this wasn't said in electronics presentation, but we will confirm like sensor wiring and addresses and pinouts and various things with them that got done kind of late last year for something. So we want to make sure that gets done earlier. Ground station, there's a new radio module, so we'll collaborate with them to write the driver for that. It shouldn't be that complicated. I don't know, ground station might already have an implementation, I'm not sure. And then we will figure out format of sending data over the radio. We have some stuff from last year. We may reuse some of it and some of it may change. So that's all just to come. And then as for payload integration, this is an even more brief overview state machine of what stuff on the payload looks like than the rocket ones were. Basically, we'll do something to make sure we know that the flight has happened and that it's over and that we're landed. And then once it's all stable, we can hand off the state machine as the payload will likely, the mission for this year, as far as I understand it, exists pretty nicely in the state machine structure. So they get some substates and we'll collaborate with the various payload subteams to write those. And yeah, so this is all to be expanded. Likely the flight part of this is simpler than the rocket state machines because it doesn't need to be as detailed. And if it works with less detail, then it makes the code simpler to write. So that is all. Any questions? Yeah, but do either of you want to talk about it or should I?
You want to go ahead?
For this year, the states are not going to be classes like before. They're going to be just functions. So each function is just going to take the data from all the sensors and based on that, make a decision on what state it is returning. Most of the time, if it's looping in the same state, it's just going to return itself. But if a straight state transition happens, it's going to return basically it's a function pointer to the next state, which will also be a function. So all the states will basically be stored in like an array with basically function pointers for all the states.
Other questions?
Anybody else have questions?
How are you planning on implementing the integration tests? Like, is that being planned with the server Sagamore? Like, how are you running those?
So I don't know yet exactly. If like the idea is that we can have a Raspberry Pi sitting in Sagamore or something that is connected to the internet and just like waits for changes to happen on GitHub and can do something with a physical board that's attached. How much that is, I don't know yet. We'll be able to upload code, and we should be able to do some like probing and communicating. The like ideal would be the Raspberry Pi can act as all of the sensors on the I2C SPI bus. How possible that is depends on what the Raspberry Pi can do, and I don't really know right now. So it may be some other way of simulating data. Yeah.
Yeah. If a state isn't detected properly on any of the states, will it like skip to the next one? Is it mention or get a timeout?
Yeah, I guess this doesn't have any descriptions. In previous years, we have had timeouts on all the states that were safe to like just assume we passed it. That is probably what we'll do again. There's an abort state here, although I don't know that it was almost ever used in the past. There are like very few cases where we actually need to like abort, and mostly it's just we can assume that we missed something and we can skip to the next one. That's usually what happens.
Okay.
Yeah.
Just an idea for the, like, especially for the payload where you want to be doing something once you can. Would it be possible? So like, let's say you abort for some reason. If you, or actually, I guess that's probably less good for example, but like, if you're in flight, if something happens and you go to abort, like, I don't know, like, does abort make sense? Because, like, if you know, well, I guess it depends on if you trust on your flight. I'm just thinking, if you get stuck like in a flight state and you abort, then payload would never use mission, right?
Right.
And so, like, if you are still even in abort, if you're still checking to wait to see if you aren't moving after a certain amount of time, like, exit abort, is that possible?
As long as we have some way of telling that the payload's like safely ejected, then sure. I wouldn't want to do it if like there's a chance the payload didn't become ejected. So,
But I guess,
yeah.
I guess an option would be, we're already planning on having managed from the ground station.
Sure.
And
Could
if
be
you're getting
that.
telemetry and the payload's in the abort stage, we do provide that.
That's yeah. I guess I didn't say that. The other things we need to do are like commands from the ground station. That kind of comes with formative data, but there will be some of that. So yes.
This exact slide, actually. I'm very curious if it might just be payload's job, but I'm also curious if it's your job. What determines when it switches from payload mission to stop?
I don't know exactly what the payload mission is, but when they decide to done, there may be actually no stop. Like I think the goal is teleoperated control, and so if it's just like the ground station can tell it to stop, or you can keep controlling it.
Yeah.
There doesn't need to be an end.
But there's no autonomous like state.
Yeah, stop isn't necessarily a state that actually exists. We may just have it be powered until it gets recovered.
The one thing we want would be a full stop or not, but if the motors overheat, we definitely want to
That yeah.
cool down.
I was mostly curious because for the other stage, I didn't think there was a stop. Just as recovery.
Yeah, it sticks in recovery. Yeah, I guess that's fair. It's probably more like that. There's not like a shutdown unless we run out of battery, I guess. So that's true.
Thanks, yeah, that's all. Anybody else have questions? No more?
Good. I don't know, maybe, I guess it doesn't. Well, I don't, electrically in space, I don't think it's. Okay, well, let me throw. Could you guys add something if we had a speaker to a payload that buzzes it so that it's doing this?
Yeah, that can be in the like recovery stage screens. Maybe not constantly. It seems like it would use a lot of battery.
No, not the laser. Daytime.
Oh,
Yeah.
Now I can learn this. Like, you know, right? Where'd you go, Mom?
Yeah, assuming a speaker gets put on the board, for sure,
Okay.
which it should, so.
I don't know. I guess the.
We had trackers on.
This is why we can't make the WEGs though, because someone would definitely steal the WEGs. I would steal the WEGs.
I don't like learning the business.
Yeah.
Yeah, wasn't any stuff. They knew to keep it with.
Okay, thank you guys.
Over here, help.
I was. I told you.
No, this was a year.
I think we did this last week.
Well, we were gonna put a JPL speaker on. So I took off.
You just said it wanted to scream at you.
Yeah, so I took off and hear the dollar price. They're going, oh, okay. I do think of it. I do think of this when it was you screaming.
I didn't know what you were about screaming at the watching.
We can have states for like, he got out to the pad and then the rocket is like.
I would actually. I do think someone has to say something. I want a speaker. Oh, what else are we can play? Let's change it off. No, I want to say. Oh. We can do this. I just actually.
A keys?
Yeah, we're gonna keep walking by.
Oh my
Yeah,
God.
that will know where I just. It's all over. Not the high is vanilla. Like
Oh, but it's. We don't want to share it.
That's a great idea. I'm trying to. Someone brought me to the ground for home.
Like alien.
We just had a time. It's obviously. Has a 10% chance for you. I watch YouTube. That's the thing you electric motors. Yeah.
No, no.
Oh, you have to buy.
PTSD unlocked.
Wait. Wait, it's got, soup filled by. Yeah, you are a good first student, right? It's got 8 kids. How loud? Not. Wait, so you can both things on it. Oh, God, John business. John business. Well, I'm just on it. If we just overhold those. Yeah, well, we see it's.
Yeah, this giant fire. Well, exactly what it is.
Brush fire, that sounds like that.
I'm not ready. Thanks.
We should have it still.
What's he gonna do?
But yeah, even, wait. Devin built the same house with over glass. Yeah.
Okay, look at the live stream.
Yeah, just.
No. I'm famous.
Yeah.
People can't get British voters.
We had this live photos.
Oh, no, let's see it.
Well, they don't have to know. No. I think that should be. Yeah, okay. Yeah. If they watch the news, yeah, they deserve to know. What's in the transcript is what I want to be the transcript. I'm gonna put that thing out there. And obviously. You know how, have you seen the thing where it's like at the beginning of the meeting, they yell like, Dinosaurs and like stuff that they do the dinosaurs and like. Jen, you got things, yeah, it's a sign, and then they had to monitor them. Oh, it's helps. That you're taking this. Oh, so good though. I would say shoot. I could still do it. We know summer. Can you guys see six? I don't think it's right. You don't have to. If I would think it's still on. Like why? It's just how to speak. I think the Rockets are JBL's gonna move.
Oh, I know, I'm sorry, wait's been taken.
Yeah. I think. I mean, not actually. It does.
Like, the speaker will be JBL's.
Strategy that
Exactly, to be honest.
It's not like in the town.
Bars.
Okay, I was talking about, you know, like, think of my, if I don't stay by my side. Let's see. We're also like I was talking about this. It's fun to be here. It's like so amazing. It's not really like bombs. There's no one bigger than that. Yeah, like they're just not. Also, you can see this. Yeah, it's like. I don't know what it would be if I was like, where are they? What's it? I go, oh. It's just everyone's like, it's like bombs on Max volume. Oh my god. Last year they couldn't even figure out last year who's I was walking like Max volume just like there for 20 minutes. Yeah, so like your radio's on and you have this story on you are press my button. And I said 20 minutes. And I was like, oh, it's hot. What's our bro, Sean, that's crazy. What? Your reply to Martino is English as well. Over in Vienna, just like dogging on myself. Like I need a builder. Was he even watching it? Oh, no, he didn't know PDR was today. He doesn't know what's a old I know a civil engineer is not talking. I'm gonna it's creation in like 10 years. Is he planning on building? Don't say that. We're saying, bro. You have a foreign door too. When I was raised here. Yes. Go get it. Oh, yeah. Be ready.
Yeah, it's like, yeah, slides on it. They're like, I have a slide out about some stuff.
Because it's my.
Just a little note for everybody.
No.
When you get to this slot, the introduction of your names aren't just like say, hi, we're the AM machine. Introduce yourselves. That's it. Other than that, it's gonna do great.
I love presenting.
Public side, I love it.
We changed their first slide in the actual presentation.
I fixed it well.
You guys.
What?
Slide number you were?
A whole.
That's good. You did that on purpose.
Except, no, one of you guys changed.
Oh, what's that? Slide one.
No, not you, one of them.
That's I changed.
Yeah, according to the.
It's also.
Next to all go like.
No, we should not.
Well.
Now, everyone needs to have legs touching the end of the table or like the equivalent side of the table. Securely. Make it go, it's fine.
No, see, no, see.
That. Wait, we got
3 minutes. No, see, that's like.
Yes.
These are not like. Nothing that was. Once again.
Is that specific requirement?
No, it has in the Discord. Like the Discord is the.
Whoa, who's saying?
They say you're not allowed to.
You can't steal our idea. I should go. So what's all right? We're gonna terminate now. Terminate the.
Get ready.
Oh.
Hi, you're gonna present, you stand up here with us? You're part of our sub team. Man, you gotta present our question slide. Come on.
Such a throwback. Flashbacks. Actually, he's a good professor. He is. He taught it really well. It's just like lack of time hidden there. Yeah. I can't. So, it was hitting him. Oh.
I don't think we need to.
Is everyone?
Yeah, we're all.
Wait, don't say yes.
The changes. That's good. We're gonna find out. He added a slide and some text, I think, for his section.
Well, I didn't get it.
That's okay.
They can be used for recovery. So they have to be actively provided.
Ready? Through that cameraman. 30 seconds.
No, that's so fair. Even stuttering. Honestly, as long as
I mean, if you guys maybe.
I had like a man that grew up in the 60s. He's also a football player. He just yell at us. So it's like that's where I was like, there's nothing.
Wait, well, I'm not sure.
How did you skills?
Together.
You can twist them and keep them these things.
That's a good reality.
Okay, well, you're still a minute early.
Okay.
Very good point.
I watched.
Okay, now you're.
Okay. Hi, everybody. My name's Jensen. I'm our 30K Rocket Recovery and Avionics lead, and this is our PDR presentation. A little bit of a timeline. A term, we got our initial CAD, initial simulations and calculations, avionics research, and line diagrams done. This term, we're looking for, obviously, PDR. We're looking to finalize our CAD, finalize our simulations and calculations, do some wiring diagrams, and do some parachute folding practice.
C term, next term, we're looking for 3D printing, test assemblies, technical documentation, and hopefully ejection testing, although that might be moved to D term. D term, we're looking for line cutting, integration, and obviously our IREC checklist. System overview. So we have a dual end, dual deploy recovery and avionics bay this year. We're doing a CO2 black powder hybrid ejection system. This is because CO2 is a lot more reliable than black powder past 20,000 feet. So for our drogue parachute, which deploys at apogee, this will be preferred to black powder. And we're doing black powder for our main deployment for our parachute, just for space optimization and cost as well. We're able to do this because our main is deploying up below 20,000 feet, so black powder is still fine. We have 3 subsystems. We have our parachute and shock cords subsystem, 36-inch drogue deploys at apogee. We have a 96-inch main, which deploys at around 1,500 feet per IREC requirements. We have an avionics systems and mounts subteam for our RRC 3+ and Blue Raven altimeters, which we'll get into later, and camera mounting systems. And we have our recovery sled, which is a polycarbonate sled with G10 bulkheads.
Hi, I'm Harry. I worked on the parachutes and shock cords with Jensen. These are the requirements for the shock cords or the parachutes. Shock cords have to retain integrity. The drogue deploys at apogee at 30,000 feet. The descent rate is between 65 and 131 feet per second, which is the IREC requirement. And then the main deploys at 1,500 feet. Descent rate of less than 36 feet per second once the main deploys. And we have to run antenna wire along the drogue shock cord. And currently the drogue deploys at apogee of 30,859 feet with a descent rate of 80 feet per second. And the main deploys at 960 feet with a descent rate of 22 feet per second. And those current specs are taken from the Open Rocket files.
This is our basic flight diagram. It has our apogee, time, altitude, range. This is from an Open Rocket and Razero simulation. Might be outdated. I made this a while ago, but it's roughly what we're looking at. So they haven't changed that much. Our main parachute is a 96-inch toroidal parachute. Obviously, we mentioned this earlier, is a descent rate of 22 feet per second, which is for the IREC requirement, works out. We have an opening force of 98 pounds force about. Packing dimensions, 4.9 inch diameter and about 7 inches in length. Because we're doing black powder, we will have to have a Nomex blanket for this one. We might be able to use last year's. We're going to look into that, inspect the parachute, but we also can just order another one online. It meets IREC requirements, so that's why we're doing it this. We also did this same model last year, so. Our drogue parachute, we're doing a 36-inch elliptical parachute, descent rate of around 80 feet per second, opening force of 22 pounds force, packing dimensions 2.6 inches in diameter and a 4-inch length. Clean injection, so no Nomex blanket needed, meets all the IREC requirements we're looking at. So
this is the pre-launch configuration of the rocket. This is what it would look like on the launch pad. And then we have the drogue deployment line diagram and the main deployment line diagram. Used a MATLAB script for these line diagrams, the lengths of the lines. Assume 2 feet of clearance between the airframes at all time to prevent damaging sections. The upper airframe remains below lower airframe at all stages of deployment for payload deployment. And the lines are subject to change, and they probably will.
For our shock cords, our main shock cord is going to be nylon. It's very similar to what we used last year. There's no real reason to change it. Our drogue shock cord, however, because we're running the antenna for ground station along the drogue, it has to be pretty inelastic to prevent any stretching and breaking of that wire. So we're looking at like Kevlar flat shock cords and Kevlar tubing. We're leaning towards the flat shock cord simply because threading the coax cable in the tubing, like in and out of it, could prevent, like that could be pretty dangerous. It could rip the shock cord, which, you know, we can't have. Moving forward, we'll be doing parachute folding practice. Obviously, we're going to decide on grounds or on shock cords with help from ground station as they figure that out. We're also looking at heat shrink wrapping and or tubing for the drogue line antenna to keep it on that shock cord, and we're going to figure out how many shear pins we need.
Hello, we're the avionics sub team. So my name is Maya. This is Matt. So here are requirements. So we need a dual deployment, completely redundant altimeters that are usable above 30,000 feet, 20 minutes of data per flight, 3 camera systems, outward facing, drogue facing, downward facing, and streamlined downward facing camera mount, battery spacing optimization, and we can't have no LiPo batteries this year because they blow up too often. Our primary altimeter that we would like to use is the Blue Raven. It's been proven to work in the past years, and it's made by Featherweight Altimeters. It's Bluetooth and micro USB interfaceable, screw mounted, and it supports dual deployment. And the batteries that use a single li-poly cell in to a 16V pack. The max altitude is 45,000 feet, and it's 20 millimeters by 46 by 12. Our redundant altimeter that we chose is the RC3 Plus. We didn't get to use it last year because things happened. And it's made by Works, and it's a different company, so it's pretty good. It's for different checks. As a USB interface, it's screw mounted also, and supports dual deployment.
Yeah, hi, I'm Matt. So we need a external housing for the camera that's coming out the side of the rocket. It needs to be capable of protecting the camera while also minimizing any drag on the housing. And we also just changed it so the camera is coming out at a 45-degree angle instead of pointing straight down. Right. These were the initial designs before we changed it to fit 45 degrees. They were pretty rough. They allowed the camera to be completely outside of the airframe and also bolted directly to the housing. There's the camera dimensions there. Right, so this is where we're at right now with the housing. It allows the camera to come out at a 45-degree angle. It has also reduced the footprint of the actual housing. It's about 4¼ inches in length right there, and just under 4/10 of an inch in height at its tallest coming out of the airframe. We will be 3D printing this. We're not entirely certain on the material yet. And the camera itself, instead of being bolted into the housing, would be either epoxied or glued with hot glue onto the inside of the airframe. Securing it, it would also allow us to seal off the internals of the rocket from the hole inside of the airframe.
And moving forward, we would like to finalize our avionics mounts and look into heat set inserts. We also want to look into screw switches and also finalize our camera mounts, and also look into a lot more wiring diagrams and batteries that we want to use that fit the IREC requirements this year.
Hi, I'm Diane, and this is Jaden. We're part of the recovery avionics sled team. For requirements, we want to be able to fit the redundant altimeter system and have a full CAD of the sled that fits the 5-inch ID airframe with room for all the avionics, and can also hold the CO2 ejection system. For the bulkheads, we want it to be able to interface with the CO2 systems and withstand all the opening forces. And we'll use lightweight fiberglass design with the flange. For the bulkheads, we're going to use, or planning to use, G10 fiberglass We'll include a flange for a coupler, since it'll help seal off avionics from any potential contaminations. Where we have two, one for the black powder and CO2. And we have some CAD models here, and some was made by Tinder Rocketry. For the bulkhead main, we have our stress simulation. We use like 50,395 elements for more accuracy. This will be for the black powder bulkhead. And for opening forces, we use 95 pound-feet. And we were able to get a factor of safety of 5.2, so pretty good. Similarly, bulkhead drogue, it'll hold a CO2 system, and we use 22 pound-feet. We were able to get a factor of safety of 22, pretty high. It's very safe.
So this is our recovery and avionics sled. It's 11.5 inches in length, and we have the redundant altimeters. It has multiple mounting sides, and the tele-GPS antenna, it's not modeled in right now, but it will be coming out of the side and zip tied along the threaded rod that we have. We'll be buying these from DigiKey and Battery Space. And it's all held together with 2 1/4-inch threaded rods, which will compress the bulkheads onto the coupler tube. The battery board screw switch will have access holes for the altimeters, and we'll be running our wiring along the rod channels and using zip tie holes. So moving forward, we'll have to finalize our avionics mounts in CAD and also add along any other systems and cameras. We'll work with avionics to complete wiring diagrams, and then we'll have to prototype and 3D print.
Any questions?
That very well.
Mhm.
But very well, like, so we may want to look at that somewhere else.
Yeah, it's definitely possible. Looking back on the thing, you can't really see it, but on the other side, there's a whole side that we haven't had anything on yet. So that I was planning for any other ground stations systems we have. I think Chaz wants to throw a board on there, I believe. So we can also probably just throw the tele GPS there. Yeah. Yeah. Mhm.
Your line diagram. Okay, so that 24-inch line on the opposite end of the drone, is that 24 inches from the bulkhead or from the top of that airframe section?
Bulkhead. It's from the bulkhead. Probably gonna need more space than that, but it's subject to change. It's we have a MATLAB script. You change like 2 numbers and it'll fix itself.
That was the thing I wanted to bring awareness to is if
Yeah.
the airframe is a significant.
Yeah, it's significant. It was a rough estimate at first.
Charges. Line is top pushing the drone, and you can get a situation where the drone deploys in the airframe.
Yeah, it's definitely gonna change a lot of that. And then when we get to determine do line cutting, we'll like look at we'll like lay it out all in Sagamore, and we can see the whole setup as it's going down. So
The lines usually change, right?
So.
I was also gonna say, I was assuming that this is a first set of line diagrams because you don't have all the parachutes, and I just want to make sure that when we're doing the actual line diagram calculations, and line length calculations are taking into account the shroud line, like for each parachute, because that is very important and has happened to us in the past. We didn't take that into account, and then even if you think that it's long enough for a parachute to completely out, the shroud lines are pretty long for some of those big parachutes.
Yeah.
Okay, that's my first comment. The other thing, just as just a curiosity, I know you're talking about the parachutes from last year. I don't know how much you looked into it, but if there are burdens on it, we did do some patching testing 2 years ago. And you can look into some of that. Well, if it is, I'm just throwing that out.
I looked at them briefly with Sean a while ago, and we couldn't find any burn holes, but we didn't really go thoroughly through all of it. So
I'm assuming, sorry, this doesn't, you don't need to go to the slide, but this is for your ANSYS simulation. I'm assuming the maximum force was calculated using the parachute opening force calculator.
yes.
Just making sure that we're updating that as things.
Yeah.
Also, I'm trying to find my question. The last thing is on slide 78, which actually, yeah, maybe we can have. Just thinking about the heat shrink wrapping, I think that sounds like maybe not the greatest idea. Because, so we did talk a little bit yesterday, PR about the fact that that line is going to have to be a lot longer than the shock cord for a couple different reasons. One of them being, keeping in mind that your shock cord, your recovery harness is most likely going to have some amount of stretch to it when it's you're ejecting things and they hit their widest point. There's going to be some sort of deformation in the line, and so if you have the wire for the antenna, like actually.
Yeah.
Like I'm just worried.
Yeah, it could.
Also related to that, I don't want it to be super tight because choices.
Yeah, we were also talking about potentially looking at doing a prototype on the lift rocket, I think, yesterday. So we could test out some different stuff on that to look into.
Awesome. I just wanted to.
Yeah. Yeah.
Okay.
Oh boy.
My name is Clay. All right, just so you guys know, making sure that the bulkheads have large eyebolts. Also, this goes for shock. For all of your eyebolts anywhere, they need to have wide washers on the other side.
Yeah, they made us buy them at home at IREC last year.
Write it down.
It's we'll figure it out. How wide? Because I can probably.
Those ones last year ended up being. There was a number they gave us. I think that was just pulled out of.
Is there a? There's.
Mine.
So there is a little like spacing with the CO2 system.
Yeah.
That we'd have to look into for that.
Try and make it.
Okay.
And like, if that means you have to put something, like theoretically, you could make a metal plate that runs the entire width and also CO2, like, that's better.
Yeah.
Like, so it's because they definitely like had an issue with that, and I'd rather not have to deal with that. And then the same goes for each shot. I know we're not.
I think we all are also having a metal plate on the CO2 bulkhead. Is that still happening?
Oh,
do we know about that? Yeah, so that'll help for that. So
but at least we got that.
Yeah.
Like an inch, maybe an inch and a half flush on it. Shoot it out. But then the other thing is for the camera thing. You guys have been writing it, so like at some point we should talk about how we're gonna smooth those layer lines out.
Yeah.
Because that will cause significant drag, so, it's definitely like, it's easy to smooth them out, but like we should just want that.
Okay. A couple quick questions about the camera. Put any thought into a way you constrain the focus ring of the camera? Because like if there's heavy vibrations, it could come into focus. I mean, we can probably do testing, maybe it's not.
We haven't, but no, that's something we should look into.
I mean, one option is to just.
Yeah.
There's also like for the purposes of like altimeters and potential like turbulent flow caused by that mount, messing up like pressure like sensing with the altimeters in the bay itself, we were pretty much probably just going to either glue the camera in there, so that could provide some type of damping. Yeah, to prevent vibrations, but we can also look into other solutions.
Yeah, kind of on that note, if it's not possible to do this, like that's not the end of the world. It would be really nice to be able to take these cameras out and reuse them.
Yeah.
Matt was ordering them today, and they're 50% more. They're already expensive, and they're 50% more expensive because of service and stuff. So if we're able, like, if you could look a little bit into some system where we could remove them, that would be amazing. Again, it's not the end of the world. But it would be nice.
I mean, what we'll do anyway is we'll make probably some type of casing that goes inside the hole we cut out of the airframe. We can look into bolting it instead. That might be more for like might cause more vibrations, but we could also put like, I'm thinking like foam or something to reduce some of that potentially. Yeah.
One idea for that could be create like a 3D printed thing that goes directly around the camera.
Yeah, that's
glue that in place.
yeah, that's basically what we're thinking.
Reprint so most of these come with them anyways, so I feel like what they have. Usually these cameras, some of these run cams that I have came with like a rubber thing that came around the outside. If you make the hole big enough, slightly smaller than that, when we put the rubber in and then screw it down, it basically clamp the rubber and things.
The other thing, honestly, one more thing about that, when you put this in, so there's a camera and then there's a cable attached to it. How are you sliding the, like, what direction are you putting this in?
The plan as of last night was to put it like basically just in from like where we would like not from the outside, from like inside out, but if we're doing like the casing, we probably would have to figure out how to put it outside in, which I think we probably were gonna have to see how it like what the camera interface is with that board, because we don't know how big the plug is on there.
Yeah.
So
Yeah, and there needs to be some way to like put the camera in and then also connect that to the
to the power system.
everything else.
Mhm.
And then also, because the camera has an SD card, there needs to be some way to, even if the camera is stuck in the casing, there needs to be some way to access.
I believe the SD card's on the board itself, not in the camera. So yeah. And so the camera wire is detachable from the board, not from the camera. So we can put the board in beforehand and then attach it after. So.
You guys, at some point, maybe using, you guys know what Wago's are, you know, those spots here, they're like, basically like one plugs in quick wire.
Yeah.
Like we splice the, I don't know, probably not. Okay. Yeah, never mind.
Okay.
That's still.
Yeah.
One thing's on slide 91. Just thinking about, or sorry, 92. For like integration, so the Mars board is going, I assume, inside the box at the bottom.
Yeah, probably.
So, one, how is this being assembled? How are you thinking?
Probably thread rods on one bulkhead first, then slide on one of the one of the sleds.
Okay.
And then standoffs, the boards.
Because I'm thinking those circular green, those are the antennas.
Yeah.
There's gonna need to be a cable connecting the Mars board and the antenna.
Mm-hmm.
So what, those are circular ones.
Oh, I'm sorry. Never mind. You're right. Never mind. Okay, so that's not a problem. My other question is, it looks like once the Mars board is in there, it's like not accessible. Would you be able to add some kind of hole so that you could plug it in? Because there's a micro USB connector on the board. Because it looks like right now, once the board's in there, like you can't plug it in at all.
We'll look into that. We still have a lot of interfacing to do
Yeah.
with ground station and EMP.
And
So
I would imagine it's not too difficult.
yeah.
Just so you're aware, because
Yeah.
we could,
also
it's nice to be able to run it when it's all integrated. Okay.
Any other questions? Okay, thank you.
Okay, this is me.
Yes. It's maybe once you point it out. Is that how it is? I don't think that's just how to. Oh, which one? You say go right or?
Given the photographs and stuff, I mean, just. Yeah.
You guys
You've seen the drums.
photo.
Change the order of the slides.
Nice. No, they say the same. It's on you. Not like that. Okay, go forward.
Might be,
Might be the beauty line.
yeah, this might be it. It's fine.
Yeah, that's pretty good.
Well, actually, you might not need 2 lines. You just gotta be like closer control. And then the other thing is that everyone needs to step forward enough that like you're in line if your legs were touching the table. So if you're by the table, like you're touching the table. If you're not in front of the, if you're not behind the table, just be in line with them. Lie down.
Oh, okay, actually, yeah. Next year, we should put the division on the table and cross lane.
Next time. Yeah, the sun is on still. Wait, why do you sound like that? I'm sorry. I can hear you. Low, I see. I didn't even know that. Wow.
Right, it's not that close. It's not that close. Yeah. It's not wrong. It's not Massachusetts. Alright, so next year, we have, take a picture for each sub team with the division lead laying.
I'll just watch it.
Some of you guys can like stand too. Because the slide, you're not blocking the slide.
Yeah, someone join me, so I'm not alone.
Yeah.
Yeah, so I think we should first. So we cycle out.
We go like.
I guess we can go with that first.
Because we can use slides, but I'll do.
Yeah.
I don't.
We still need to say our names.
Yeah, it's just.
Alright, you guys are ready to start.
Sweet.
I want to ask my thing, please.
We are two-stage structures. We are two-stage structures, and this is our PDR presentation. So a little bit of an overview of what we're working on. We have 3 different subsystems that we're working on. We have the rocket coupling, the payload coupling, and then the motor retainer.
the rocket couplings seal off the avionics bay and they connect the body tubes together. This year, we'll be designing two different types of size diameter couplings. Two couplings will be on the 5-inch diameter sustainer, and one coupling will be on the 6-inch booster stage. The payload coupling will secure the payload mechanism, which will be on the sustainer stage of the rocket, and it will need to fit the 5-inch diameter rocket size. The motor retainer ensures that the motor is fixed in the rocket and that it can withstand the heat caused by the propulsion of the rocket.
Hi, we're the rocket coupling team. I'm William. I'm Kaden.
I'm Thomas.
And for the design requirements of rocket coupling, it's basically just to connect the lower airframe to the coupler tube on both the booster and sustainer stage. And while doing that, maximizing it in the diameter for avionics and air brakes. And like Josh said earlier, there's two different designs. One is a 6-inch while the other one is 5-inch.
This year, we're considering a new design where the rocket coupling is one single part. This part will be radially bolted to both body tubes, and it requires the bulkheads to be surface mounted to the outer face of the coupling. However, it still allows for two bulkheads to be mounted to the couplings. This part will be made out of 6061 aluminum and machined on the 5-axis plate. The gaskets between the bulkhead and the couplings will be laser cut out of rubber silicon. And this term, we will be simulating and doing hand calculations to ensure that the bulkheads can support the parachute loads when surface mounted.
So we did an initial preliminary simulation testing using some values from last year. And the goal was to just get an initial idea of how stress would be distributed through this new coupling. And we can see that because we're surface mounting the bulkheads, the stress is focused primarily on the tabs and on the center diameter of those screw holes. Realistically, the stress is going to be on the screws and the threads. So this isn't a perfect demonstration of what it would look like. So we'll be doing a bunch of more further calculations and simulations to really understand how the stress would be distributed and to make sure that we have a reasonable factor of safety. And we can see that the yield strength is 3.989 times 10 to the 4th. And then the purple arrows are the force, which we used from last year's calculation for the parachute force. And the green arrows are the fixed cup.
All right, so some future improvements is that we could consider a method to clock the bulkhead into the coupling rather than just placing it on top. And we can consider using fasteners, but if we want to remove the bulkhead, then that may be a problem. And removing the radial bolts might wear down the tolerance of the holes on the rocket's body tube over time. And in the future, we will do calculations of the bulkhead strength and its overall ability to stay together.
So this is a potential design change that we're considering. And so for the upper avionics coupling and the booster coupling, only one bulkhead needs to withstand a significant force. So we could redesign the upper, in this case, the upper bulkhead to be a slightly smaller diameter than the lower bulkhead. And that would allow us to fit the bulkhead through the bottom and then screw it inside the coupling, which would help distribute the force. And that would require us to kind of change the dimensions of the tab so that the diameter of that is smaller. But if we were able to do that, then we would kind of avoid this issue of stress that we're currently needing to look into. But this requires us to work with recovery and mechanisms to make sure that our parts or the redesigned bulkhead will fit all of the parts that they have to make.
So we are Payload Coupling. I'm Anthony.
I'm Matthew.
I'm Jack.
And I'm Nate.
This one. So design requirements, what we need to do for the rocket is to be able to protect the payload bay from any pressure changes caused by the ejection charges and air brakes, make sure that they aren't falling off, and then fasten the payload recovery bay to the upper airframe. And
So both our nose and payload couplings are gonna remain mostly consistent with last year's. We are thinking of increasing the radial bolts from 4 to 8, or no, from 6 to 8. But we're gonna have to run calculations to determine whether that is beneficial. And then we still need to reach out to payload to determine whether our dimensions are compatible.
So for the nose cone, we're going to be using, instead of screws, we're going to be using 8 spring pins. And also we're going to be epoxying the nose cone coupling directly to the upper airframe.
All right, so it's the couplings are mostly the same as last year, but there are some minor changes. So we are going to do stress analysis to make sure it can withstand the expected loading. So that means hand calculations and then simulations on that. And then once we're sure of the design, we'll machine it out of aluminum, and the gasket will be made out of rubber laser cut. And yeah.
All right, we are the motor retainer team. I'm Ollie.
I'm Evan.
And some just basic requirements first. The main objective is to hold the motor and the airframe together. We want to ensure that the motor does not shoot through the rocket, obviously, and also that the actual retainer itself can withstand the heat from the propulsion. And this year, a new requirement is that it has to connect a 6-inch diameter airframe with a 5-inch diameter motor. So some more in-depth overview. Like I said, last year's dimensions were compatible with a 5-inch diameter and 5-inch rocket, whereas this year it is updated for a 6-inch body tube. Because we're using the same motor, because we purchase it outside of the club, the dimensions of the 5-inch diameter are the same, which allowed us to reuse a lot of designs from last year, and we were able to modify them for this year's rocket as opposed to starting from scratch.
So here's some in-depth look at the motor retainer design here. And as you can see, the upper diameter has changed to reflect the new 6-inch requirements here. Since last year was 5-inch diameter, but now we have to update it for the 6-inch. And as you can see on the top half of that side view, the top diameter is 6-inch diameter, but there's a lip for the body tube to sit on, which will be interfaced with 10 spring holes. And then for the bottom half here, it's still 5-inch diameter. And this is the part that's holding the motor retainer in place with 12 bolt holes here, 8x32 hex screws through. And this is the same motor retainer as last year, the one we purchased, 98mm retainer flange covered with a cap. And here's just a section view of the motor design. As you can see, there's 10 spring pins, 0.626-inch diameter. There are 12 bolt holes with a 0.136-inch diameter, and same as last year, 90mm retainer. And the lip for the body tube to rest on is 0.085-inch diameter.
So moving forward for structures, the main objectives for B term are to begin doing some more advanced calculations to test epoxy shear stress, radial bolt stress, simple and complex tear out, and then bulkhead strength tests. We will also be doing some simulations in ANSYS to test our current designs, and then based off of the information, we will be finalizing our designs and then doing a final round of simulations. And we will also be 3D printing our designs so that we can make sure everything fits together. And then ideally towards the end of B term, we'll be working on some CAM simulations and planning how we'll machine couplings. Any questions?
I did notice I was doing some fine print reading for the radial bolting
Mhm.
stuff. And also just anything that seals. I just want you guys to consider the fact that temperatures that we're launching in vary greatly. I know that this rocket isn't going to Iran this year, But in the future, I think we do want to bring a two-stage rocket to island. And so just considering that we launched in February in Vermont and then in June in Texas, those are very large numbering differences. And so just taking into account that the ceiling is going to be very different. All of the metal parts are going to crack and expand a little bit. So something to consider.
All right, start at slide 101. All right, first off, just I didn't catch this in show me. Just so you know for the future, when you're fixing the stuff on the outer edge, that outermost flange shouldn't be fixed.
Oh, okay.
Because like there's nothing fixing it in the actual rocket, like it's at the mercy of the cycle above it.
Gotcha.
So I'll make your simulation more accurate. As well for the, we already talked about that, that's good. I'll just say it just in case. When, for the newer coupling, you guys are doing simulation on that. Make sure that when you do the load, it's distributed over the plan.
Right.
For 102, yeah, the body tube wear is definitely gonna be a big concern. As well as just like making sure we can cut the holes well. Last year was not, I don't want to say it didn't work, but like, it didn't work. Like they ended up making the hole way bigger than it.
Okay.
You could not get a good hole cut in like the right place. So we definitely need to look into making, like maybe doing some test cuts and seeing if the holes actually end up where we want them to be.
Makes sense.
We can talk about that more. I just want to make sure like that should be like, that's one of the more major concerns on this list. And then 106, no, I mean, only thing check this on them. Pretty sure the upper payload coupling doesn't actually need a gas.
Actually, I think it has in there.
Yeah.
We wouldn't need it. Unless the mark board is gonna be.
Well, the mark board's in the payload though, isn't it? So it's gonna get blasted anyway. That's what it's supposed to happen. But then there's nothing in the nose scope, it's just the GPS tracker stuff, so I don't think those.
Yeah, that should be fine.
Okay, then yeah, you guys don't need a gasket on there. I mean, like, if you want it.
We started a new design that like cut down on weight without the gasket, but we didn't finalize it for PDR.
I'll get that. But yeah. And then the 1.6. What was the reason for increasing the?
That was more of a consideration when the sustainer diameter was 6 inches, but now that we're going back to 5, we'll probably be okay just keeping it the same since it worked last year. But we'll do some testing to see.
Okay, also, yeah, well, we should definitely do that. For the, I didn't say for, oh, okay. 107, job I wrote for chance. Is this 107?
I think so.
Which 108? Try 109. 110. You know, okay, I guess it goes for both of them, but I would, this kind of is a two-part question. One, I would definitely look into possibly making the flange bigger on that motor retainer. I know that was the size we had last year, but we also had a much smaller casing last year.
Okay.
So it's gonna have a lot more momentum pushing against it when the parachute ejects. And then as well, for your own peace of mind, I would probably look into using bigger spring pins than what we used last year because they were really annoying to use because they're so small.
Yeah.
And it can make the flange harder. That like we had to choose that size because of how small we made that flange, which like worked, but it was just really annoying to use. So I would definitely look into that with you guys and maybe like if anyone I think they're actually looking at because there's a lot of different types of spring pins. So
okay.
Yeah. And then I already said.
Actually, I have a follow-up question for that, which is, I assume you haven't done that whole bunch of regulations, but how did we arrive at 10 spray pins? That was for slide 111.
That was just more of a theoretical.
We're not going calculations, we're gonna figure out how many.
Yeah. We just assumed that it might have to increase with like a bigger diameter.
I'll just say, I love how this looks. I don't know why the chamber just does something. But like, just, you know, this probably just gonna be more. All right, once this was freaking off, I feel. So it looks cool. Yeah. And so, I'm just like, you know, if I would be a little more in my machine, but like, if you could do it, that'd be cool.
Mhm.
So, just so you guys are aware. I think that was all my questions. Yeah. Anyone else have a question?
Yep.
On the single coupling design, what is the reason for having the middle band, that's the diameter of the outer tube, be of comparable length to the old design? I know the old design you had to have that.
Yeah.
For bolts, but is there not a reason that that could be made shorter for weight and space savings?
Yeah, so that's what we're considering, is maybe making it just like a tiny band, but we want to make sure that changing the like length of the rocket by a couple inches doesn't affect anything.
And also kind of a suggestion of a thing to look into. For some of the joints where you're still using spring pins and epoxy, have you considered any kind of not just kind of passively applied to like rubbing up with sandpaper, but actually machined profiles to aid in epoxy engagement? Something that you might want to look at is some of the smaller aero packs that don't have the flange. They use like a ribbed profile to help the epoxy bite down.
Okay,
That might be
yeah.
a helpful thing to look into for those kinds of parts.
Yeah, that's something we haven't considered, but we will definitely look into that.
Because like, I couldn't find a lot of some using epoxy and spring pins.
Think that would be an issue, yeah. You can also maybe just, if you want to have a clean band, spring pin level and do everything above and below.
You said you guys wanted to know if the geometry had to change for the payload bulkheads.
Yeah.
I think the only, like, the outer part we're fine with, the only thing that might change is the location of the eyeball.
Okay.
With the L channels be the same.
Sounds good.
Else? Bye. That's all. Okay, thank you guys.
Thank you.
Oh, you were seeing. Find that, you made it, I know.
Just before we start.
That's what I saw.
How do I go back?
Present name we're looking for.
There's where the, no, it says, yeah, I'm just going back to present. That's presented.
Yeah, where's the present button?
Sorry, did I just mess up the?
There you go.
Okay, cool. We're just, well, yeah, there were a couple of updates that have happened since the.
It should be updating like as we go. So, yeah. I know, I'm gonna reshare it. Do you want to just quickly, is everything good?
I mean.
Gabe, take a look at it. I don't know what you updated since later on today.
Good. I'm just gonna, just checking in.
I see you put in the CO2.
Just checking in for speaker notes. Yeah, okay. Okay, all the way updated.
Yeah, it's like, cause what's nice about PowerPoint is it does update as you go, even if you're presenting. So.
Okay.
The big.
I think it's the, no, it's, yeah. Okay.
So then we just go to her. That's not the photo.
I know. Oh, you just said multiple. No worries.
We got another page here.
What are we gonna do? Picture before we start.
I'll two of you.
Oh, yeah.
Wait, keep going forward.
Keep
Yeah.
going forward.
No, it's actually down.
Keep going forward.
Laura? Oh, I know. Probably like the most one, for being honest.
Our picture's gonna look like this.
Between the two of us, yeah.
This is more about Derek White than it seems.
So you ready? Yeah. I'm sure them just. Do
Derek White.
you want to open or do you want me to? I'll open because we're slides. And then I think it's to you. Yeah. You get on this. From the start of
That's really
So I got the parachute race, parachutes.
A hard goodwill find on 10. Someone's gonna find me like, bro, that's good.
Okay, we're ready.
Sorry.
Oh, you can't
Can't start?
Oh, darn. Come on. You're telling me I could have sat on my couch for longer? Damn it. I did not mean to hit that. That kind of hurt.
I know.
You know what? I might need the entire kit. Okay.
Yeah, if there's any eye drops, I'd just like to drink that. It's distressing. God.
I was full of
What is this?
So we have what, 9 minutes?
Yeah.
Let me look over what I have here.
So they started with this.
This is just real simple, right? There's nothing special about this.
Yeah, if it says read off slide, just read off the slide. The note is honestly more.
This I checked the document this year and they said same as last year.
Okay.
So I'm gonna make a note of that. That's
Or you don't need to make a note of that. In the thing, it's just like if that's something that
They should know about.
Yeah, I'll just say
then yeah, and also it doesn't really matter to us when we eject, so long as we know we eject.
Yeah.
So
You want me to do
the thing, I believe I might be in on that. Actually, we can just.
Oh, sorry, man, we're definitely wrong. That's the next link.
You didn't see any pictures.
Yeah, okay, yeah, so I'll take that. So the.
Oh my God, you see pictures?
The Google Sheet.
Yes, you do.
Yeah, the new one that you made for the ejection?
I have a picture for you.
I haven't made a new one for the ejection before. This is from the old one.
Yeah.
I think you made one.
I had assumed that the force in the bulkhead was something that we calculated from it. It is, as you can see, you're only dependent on the shear pins, and I can feel everything, so it just goes to other things down there.
Gotcha.
Yeah.
Yeah, at our meeting this week, if it's just me and you again, I'm gonna come to you with some questions about what everything is.
You can
Because
do
like,
that either way.
I've been trying to look up some stuff.
Yeah.
And I'm still confused about how some things work, what goes where, things like that. So
Yeah.
I just want to have a full understanding of what we're doing.
And also just, so the.
Were you online and all that?
The real reason.
What is that? No.
Like
Online is
CO2 and increasing CO2 in like CSU versus backpowder. These backpowder becomes from Hawaii. That's 25 feet.
Oh, it does. Okay.
Yes, yes, and that is we are operating.
Yeah.
Yeah.
Okay.
Okay.
All right, how's it going?
He made it. Yeah, we got another member. Do you want to redo the picture? We got another member with us now.
Yep.
Oh, did you guys already present?
No, we already took the picture for you.
Looked a lot better in person. But
Table.
You can feel it up there, like lost, like. So, like, it'll fill up there.
It's a good thing or you?
No, it isn't good. No, I've been, yeah. But so it'll, I've been doing it specifically, so I can.
That's why.
That's why.
So, what you do both sides? I'm going
I'm gonna give you, so all of these have names on them. All of the computer slides. I'm gonna give you all the black powder. So all the black powder theater too.
Oh, wait, just do that. No, wait.
You'll get a parachute release off.
No, wait, no.
Oh, no, you got the parachute.
I probably so I'm doing both.
You're doing the CM. Oh, so you're having the CM too.
Oh, so
I'm not talking about assumed if it doesn't work.
okay.
It's just, you can read off of, you can just read off of here.
Okay.
Yeah.
You don't have to worry.
You can't really readjust the names right now.
That's, yeah, no, that's fine.
Oh my
I'm
God.
gonna
Will.
just be the first, like, the first few or so slides and then this slide. And then it'll be.
And I have that one as any start and then, okay.
Yeah, so.
Yeah.
You get it up into this.
Yeah. And then they're gonna be questions of
It sounds like he's actually pretty excited.
if
Think of the capability
network you're confident
that you're
in, like, what they're asking, like, you're encouraged to do it. If not, I'll hop in. Yeah, when I did this last year, I personally got like stressed by the last questions, so I just like ripped forward and like turned to something last year, so like I am ready for most of the questions. That should be good.
There, they got the legend.
In fact, you can see the video.
We started.
It goes backwards like
3 minutes.
Yes. We're also going to, so we are kind of, we're double booked in this slot, so it's.
People always say, "Oh, that's the fun ever." You know how much it costs?
Payload R&D.
$50.
Which basically just means we're
Which is spirit following.
try and keep it.
And I asked the person to have this out. All they had left was women's awesome. The fact that they did that all crazy.
Very.
The fact that I like, and that like.
You say he fits good.
Yeah, I'm like kind of impressed.
How did you, I'm sorry to overhear conversation. Did you hear you say you fit into a women's small?
Jumpsuit.
How did you do it?
Jumpsuit?
I don't know.
I'm women small.
How did you manage that?
You can share my clothes.
This is gonna be interesting.
I will.
The slides,
Yeah.
slides here, description that is here.
Wait, so by number, which slides are we reading through? So I don't get.
127. You know, there will be a slide that just says questions.
Okay.
And then that's it.
Yeah.
Okay.
So they really care.
No, I think I'll be ending it anyways.
Okay.
You'll be all set there. Are we expecting anyone else?
No.
I don't know.
Okay. We have like what, one other kid that's supposed to be in our group?
There's two of them.
Two other?
I believe, although there was a lot of like, I think we only saw each of them like maybe twice.
Yeah, so there's like big questions. I shouldn't be here.
Which communications are communications.
Well, it doesn't help that no one responds to that group chat. Like I was sending Slacks to it, and I'm like, great, I'm having questions about the PDR. Like, no one's saying anything.
Sorry.
No, you're fine.
It's mostly anything this week and then,
Guys,
it is what it is.
I saw your Slack for this.
Yeah, no, it was also, I thought that I had sent out a, Outlook invite to everyone, like a day or two before. So I was really surprised. And then we checked, and then really. So it was just like a, hey, you have like, let's get over here. Like, I was felt bad for putting that expectation in.
The other reason I was at that meeting was because I didn't go home for break, so.
Yeah, that was also like a.
I also didn't go out that meeting until like.
Oh, so ready.
We're ready.
Full of 3 people, we are Payload Recovery.
Our goals for this year are basically the same as last year. We're just building on it. We're researching and prototyping a black powderless CO2 ejection system, as well as a mechanism to release the parachute upon landing, so that it doesn't drag us around across the desert. As required, we're going to be picking a parachute to maintain the desired descent rate, so faster than the rocket. And finishing work on the hexacopter also falls under our purview. Our timeline thus far, we've been researching and deciding on the CO2 parachute system. We're going to be getting our calculations finished over the next week or two, and then prototyping testing as throughout the rest of the term. C&D term, we're going to be manufacturing testing as necessary, so we can be well and ready for IREC.
Okay. So overview of all the events we have. The altimeter's fire signal to E-match or mechanism, at least it's the CO2, is the first thing that happens. And then we have ejection of the initial at 13,000 feet. Also, I apologize for this. It's my first year doing this. The recovery base stays in the rocket, along with the piston assembly. We have about a calculated 22 feet per second projected for the landing of the rocket speed. We're aiming for a smaller parachute this year for less chance of it being caught on the ground. And then the parachute releases on the landing when we send a signal from the payload to the mechanism or the E-match to release the parachute. Yep. Okay, so the sled for our recovery bay, it's going to be about 3.9 inches tall. The body is 26.75 inches by 2¼ inches. We have two altimeters. Both were used last year on the rocket, the Blue Raven 4 and the RC3 Plus. We also as well have two Arduino Nanos. The sled design from last year is pretty much the same. We've made a couple changes, but the middle section can hold about two 23-gram CO2 canisters, which allows for the CO2 ejection mechanism to be redundant if one mechanism fails. So we have a backup. On the sides of the recovery bay, the sled has space for two battery boards, the Blue Raven 4, the RC3 Plus, the two Arduino Nanos, and a spot tracker.
So for our expected ejection forces, we're looking at around 300 pounds. The calculations seen on the slide are from a calculator made now 3 years ago by previous recovery teams and are rough estimates. This is in part because they aren't calculating for exactly 300-pound forces, as well as black powder calculations are more reliable to do than CO2 because the black powder will hit its peak pretty consistently and quickly, while the CO2 takes a little bit to build up the pressure inside the rocket. With CO2 testing, we're just going to have to be more careful and test it more to make sure that everything is reliable, and we won't have any trouble breaking shear pins and ejecting from the rocket. For the piston, we're going to be keeping with last year's design, which is going to work to also keep the payload locked in place as we go up. Although the inner radius isn't constant, as you can see in the diagram, it's around 2 inches on average, which has a packing volume of 50 cubic inches. We'll just be putting the parachute in with the release mechanism on top of it, and then shock cord on top of that as well.
Okay, so for the black powderless CO2, it's going to be an ejection system that we're planning to improve on a spring-loaded mechanism that pierces with a pin. This mechanism will probably be similar to the Eagle CO2 system, except the spring provides the acceleration instead of black powder. One thing to note with this is the whole assembly would not be underneath the bulkhead like the Eagle, only the canister would be. All right, for the next part, our most likely plan for the CO2 is to improve upon last year's design shown on the slide, which is based on a spring-loaded barrel. The spring will push down on the puncture pin with a force of 40 pounds. Assuming the tip of the metal piercing steel screw is 0.01 square inches, the pin will exert a pressure of 4,000 psi on the puncturable top of the CO2 canister. The puncturable cap is 1 to 2 millimeters thick, and our pin will puncture we'll puncture at 1/8 of an inch or a bit over 3 millimeters. Inside the CO2 canister has a pressure of 800 psi at room temperature and 2000 psi at 120 degrees Fahrenheit. The servo arm occupies the lane down, and the pin arms sit on an angled surface ready to slide once the servo arm is rotated out.
So we have 2 parachute release options this year. Last year we had 3, moved it down to 2. The only one option that was still from last year is the Eli. On the left is the TD2. This is a great option for us because we already have one of these, so we wouldn't need to buy a new part. The only drawback with this is it does use E-matches, which means we'd have to send wiring down the payload. This is not great if we have a long shot cord. In addition, we would also need to send a signal for the release. On the right is the Eli. It disconnects on landing. It breaks apart, but it's held together until the landing, where the spring pushes the red metal pieces apart. A little bit more in depth. The Eli is 10 centimeters long. It has a diameter of 2.3 centimeters, weighs about 100 grams, and the maximum load it can tolerate is 100 kilograms. How it operates is initially the red mechanism is held in place by the black plastic case. A pin is pushed by the right part of the case that holds the left part in place. When tension is applied to the mechanism, the parachute is deployed. The right part of the case is pulled away. This allows the pin and the left part of the case free. The tension applied to the mechanism by the parachute keeps the payload in place, but when the tension is lessened, the parachute hits the ground and a spring separates the 2 sections. One big advantage of this, it is fully mechanical. It does not require a release or a signal, and is very reusable for testing purposes. We have 2 versions we are looking at. One is rated for 100 kilograms, one is rated for 50 kilograms. The 100 kilogram one is a little bit different. It's 100 millimeters long, 23 diameter, weighs 100 grams. And the 50 kilogram one is 80 millimeters long, 19 in diameter, and weighs 50 grams. The only problem we've had with these is we do not have one. And the company that makes these is in Estonia, and they have not been very responsive to our messages. So our plan is if we go with this, we would be working all specifications off of their website and multiple prototyping rounds to design our own using CAD software and 3D printing. The other option is the TD2. It weighs about 100 grams. The max initial shock load it can handle is 2,000 pounds. The max release weight is 1,000 pounds. And as I previously stated, the E-matches release this pin at the top, and this bottom part breaks away. The dimensions is it's 3.75 inches long, and it's about a 1.06 inch width. And then getting to our parachutes, we're aiming a little bit smaller than last year so we can have a faster descent rate. The main parachute we're looking at is the 36-inch rotating star. And the other option, our secondary parachute, is the 36 compact. We want to have a faster descent rate, as I previously stated, 22 feet per second, as well as we want it to not get entangled with the rocket. The nose cone weight is expected to be 8.5 pounds. From their respective websites of both of these, the Rocket Man has a descent speed, of 25 feet per second at 8.7 pounds. And the Fruity Shoots claims to be a speed of 26.5 feet per second at 8.5 pounds. In regards to where the parachute will be attached to the payload, we expect everything to be the same from last year. The eye bolt will be positioned on the payload facing side of the nose cone bulkhead. We will also run the shock cord along the side of the payload to the piston cup, which will house the parachute release mechanism along with the parachute itself. Any questions? Yes.
Two things. First, just purely a comment, the Eli mechanism is like the coolest thing I've ever seen.
Oh, I know. I hope personally we go with that one because I want to design it.
We have 3 minutes for questions, so let's.
And real quick, on your flight profile, I think it was 1,500 feet for main, and 1,300 feet for payload deployment.
Okay.
Do you have data confirming that the main would be reasonably stabilized and settled down so that everything's at a predictable rate at that point?
We've deployed that like every launch.
Yeah.
The payload's coming out of Maine no matter what, so.
Yeah, I took those numbers from documents on the SharePoint from this year and from last year, so.
You don't buy a parachute from Rocket Man. If you buy a parachute from Rocket Man, you literally have to buy it like this week.
Okay.
Because they take forever to come.
Good to know.
Or like if you order it right now, it might be here in April.
Oh, okay.
Just be aware of that.
All right.
He's more than in the United States. But it's-
He's lazy.
Between the two.
Yes.
Also, can you go to slide 123?
120. Yes. Go load.
Yeah, keep it simple.
Okay. Oh, not too far.
In terms of the system that we're designing, how are we testing this? Where are we testing this? I know you mentioned some very specific calculations. I assume these are calculations you've done. Are we going to try and measure those forces to make sure that it's actually generating the amount of force that we think it's going to generate?
So for force generation, we would look to test that. A good chunk of this, the specific map was taken from last year. And we would look to update this design more from where it was from last year. I don't have a place in mind for where we're going to test it. Yes, and would also, a good chunk of it would be testing like with ejection tests.
I have a quick question. So you said the max load is 100 kilograms. Is that, like, what is that for? Like the max load that the system can take?
That the EOI can take? Yes, I believe so.
Well, because my question is.
Not our expected max load.
Well, my question is, so kilograms is mass.
Yes.
So is that? Like what, because that's mass, but then there's the acceleration.
Yes.
Kilograms of force.
I thought it was max. Oh, because that, okay. Well, because I was just looking at the Ender Descender max loads, like an order of magnitude higher.
Yes,
If we're comparing it that way.
yes. I don't believe we're expecting to get like anywhere near even this much, and I'm assuming.
But yeah, I'm just thinking like parachute opening forces.
I haven't looked into those specifically. We can calculate, but
Yeah.
okay.
Any questions there? If you have any other questions, put them in the, the form that's in there. Okay.
Thank you.
It's a test.
Oh, but it's custom made.
No problem. The gym they showed us.
Hey, Jared, take a photo first. Center yourself with the projector screen and stand so you're not to the thing.
Yeah. Oh, wait, is that because like, well, yes, well, because what would make sense under gravity, but during the parachute opening.
Alright, this is Payload R&D. So our sub-team goals is for next year to allow the rover to drive autonomously. So we're primarily looking into sensors and methods we can use to detect obstacles. We plan to test sensors to be able to go autonomous next year. Additionally, we plan to create a testing rover to be able to bring to IREC for on-site data collection so that we can get data with these sensors that can be used during the year.
The main reasons we need these sensors are for the different kinds of obstacles we will encounter at IREC. The obstacles we have found have been determined from pictures and from IREC this year. So the first one being small rocks. The rover should not need to worry too much about small rocks. Being able to get over them should be fine, but we should still be able to detect rocks in case we come across any and in case they are significant. Small vegetation similarly will not significantly impact the rover and can likely be ignored. Large bushes are our main concern. Different spots in the desert tend to have a lot of these. So if we land in an area with large bushes, we want to make sure we can navigate around them. And one of the reasons we're looking at a lot of different types of sensors is because the bushes in the deserts are not necessarily easily distinguishable from other surfaces. They're not always green. They are often dead, so they might look much like the surrounding area. Our timeline this year, in A term, we mostly did research and create a list of sensors that we are interested in. This term, we are looking into purchasing sensors and beginning testing. In C term, we're going to continue testing and shorten our sensor list down to our most useful ones that we might consider installing on the test rover. And in D term, we are hoping to install the chosen sensors onto the test rover, and depending on how timing works out, potentially look into software.
Now on to how we determine sensor selection. So we were primarily looking at two different categories of sensor. So we have distance sensors, so stuff like LiDAR and ultrasonic, and then we have imaging. An outlier to that is a time of flight camera, which technically does both. It's both a 2D image of distance, which is really cool. So we constructed a list of what we think our top candidates are for purchase, as well as some auxiliary stuff like an adapter cable as well that we would need for the machine vision one. We need to integrate that with a Raspberry Pi Zero if we chose to, or rather when we choose to test that.
And as for testing, we came up with a hypothesis for some of our evaluations. These will almost certainly change once we actually start testing. So size, weight, power draw, how useful is the data we're getting. And then for more specific testing, we want to try just pointing some of the sensors at bushes around here, seeing if we can actually see them at all. And then testing more specifically for other terrain types and some more specific tests for each sensor type, like the smallest object detectable for some of the distance sensors, and for the distance only, could we possibly create an array of them to get a cheaper option for 2 or 3D? And because we're considering thermal and a distance sensor, we also want reference images for what those could look like. The image on the left is not the sensor we're getting. The image on the right is actually from the Time of Flight camera website we're planning on getting. We were kind of expecting that.
Right, anyone in the room have questions? Nobody?
This might not be a straightforward answer, but what factors do you think you'll need to recreate to test each of the sensors? Like what's gonna be most important for each?
Yeah. So the main thing around, for most of them, it's relatively simple, and that's just finding like dead vegetation similar to what would be in the desert. The nice thing is it's going into winter. I think we'll be able to find a lot of dead bushes and things like that to test with. With the thermal camera, it's slightly more difficult. And so we may not be able to do testing until later on, but we're mainly looking for potential temperature differences between bushes and the ground. And so that'll be harder to control for, but yeah.
And just to add on to that a little bit, like what would be nice to test as well is also conditions as well as durability. I mean, we need to think further along down the line about how best to demonstrate that, but we definitely need to like understand how the sensors respond to dust, to heat, and to vibration, considering they're going to be blasted in a rocket, you know.
Yeah. I understand. Yeah, theoretically, if we grab the bush while we're hiring this year, would that be useful? Because I can do that.
Dying just to
What's already dead?
When it's still disintegrating.
It's
Like,
a,
year later, but it'll still be like.
it's a considering the plan is currently to bring the sensors to IREC.
Oh, you
For now would not be necessary.
Yeah.
I just really want to. I mean,
If you would like to steal a bush, feel free though.
It's like what you can see why then it's like.
Both the strangest things in Chinese.
Regarding software, I know you haven't mentioned it too much. I know you're still looking into a lot of things. If you get to the point where you want to write software, and it's possible, I would consider trying to write code with like computers that are being used this year. Again, if possible, if there's works available, if you have the time for it, because that would mean any code that you write this year you can reuse for next year, if that's possible. My only other question regarding the thermal sensor, have you looked at all into like the difference in temperature you might see in objects? I'm just thinking it's really hot. Like, are the objects different temperatures enough that you would actually get?
Yeah, so this picture on the left here, you can actually see it's a similar desert environment, and the bushes at the bottom are distinctly different. And so that's why we actually chose that image there. And so we think that we're not sure when, like time of day, this image was taken, but we think that the bushes would be a different temperature than the ground, either because of color or airflow and surface area. Yeah.
That's why we want to test it.
Yeah.
You don't know what the numbers. -6 is no way.
Yeah.
I mean, it's in the
Well,
sky.
I think it's just saying the sky is negative, so I think it is.
Sky's a lot lower.
Is it maybe like not taking the temperatures and like a certain distance away?
That might be. I'm not sure what the range on that is.
I'm just curious.
Yeah.
Oh, do you think you're gonna do like runtime testing? See if like any of the sensors overheat after running them for like 5 minutes?
Yeah, that might be necessary, especially considering environmental conditions. So yeah, we'll definitely look at that. Might also go along with power draw, because if there's relatively low power draw, I wouldn't be as concerned about overheating. Yes.
We get like an oven. Then heat lamp.
We're looking at using an oven. We're at other stuff already.
We have a broken toaster oven.
Yeah.
Okay, again, a serious question.
Sounds like that. I'm serious about environmental testing. So that, and I'll
You want to take that or?
Yeah, we wanted to get first off, they're super cheap, and we wanted a better understanding of what each one could do, if one was maybe better than another.
Yeah, because also, yeah, I shouldn't say, the objects we're trying to detect are really not solid, and so it's kind of outside the use case of most of these 1D distance sensors, and so we think their behaviors may differ trying to detect something that is like looking at it, it's mostly air. Yeah. Yeah.
I forgot we used that. That is a regular word.
Did match the case?
It's fixed, it's fixed.
So that we don't block the projector. Yeah, just so we don't block the projector. So, yeah, probably the other side.
Yeah.
Cool. Is the order good?
Wait, so late. I see it. I thought that you did this. You had, wait, Laura, it's also more than 3 L.
I think I might. I'm just.
No!
Sorry.
Wait, I did.
I can.
Yes, I know you did.
I just wanted to get, I think what happened.
Okay.
I always just put like.
Is Laura gone?
So it's
Laura-
just repeating.
Camera's
She probably went to the bathroom. How dare she leave?
Speaking of which,
There she is.
you guys have to take a picture, by the way.
Okay.
I think you put my name forward.
Okay. Do you want the full story or do you want? I forgot to match case and I forgot.
It was natural to put it in lowercase though.
I didn't do that.
That was natural instinct.
I'm now making every.
You're already presented. Move up, so if you're behind the table, your legs are touching the table.
Okay, is it
On
good?
the Table, you're in line.
Yeah.
Your will is capital.
Yeah, wait, Matt, can you just move the slide?
I would rather have all of the wills be capitalized than my name not capitalized.
You put an extra L in your own name. You wrote Will.
Actually, no.
I mean, once I auto completed every other shot. Got it.
It's out.
Yeah. And when you said it's running. So that's the instruction. Now remember to be totally like going to. I'm able. He's twisting my words.
We have a presentation on your chemicals.
You guys ready? Nice. So, hello everyone. This is Payload Actuation. My name is Steve.
I'm Justice.
I'm Aisha. I'm Lily.
I'm Nithya.
I'm Nate.
Nice. So, for right now, we're going to first start off with our sub-team goals. So, our goal is to create a system that can withstand the load from Rover, from basically contain the mechanism of Rover, as well as withstand the forces of launch, as well as during ejection. So, also is to develop an efficient system for the antenna so that it can be stored as well as actuated. And then finally, to create a system that is easily integrates easily with Rover, as well as with the structure. And first, we're going to start off with timeline. So during A term, we mostly went over basic CAD as well as brainstorming. Then in B term, we hope to further refine our CAD as well as do testing of our system as well as preparing for CDR. And finally, finalizing CAD and manufacturing a final assembly at the end of C term, and finally D term, kind of just integration, final testing, and IRAC preparations. We're going to start off with the release mechanism. I'm going to hand it off to Justice.
A majority of the release mechanism will be positioned behind the rover to allow them to have as much space as possible, except for an aluminum rod which interfaces with a door handle of the hatch to keep it closed. We've placed a 1:1 gear ratio between the servo and aluminum rod to make sure that no force experienced on the rod damages or deforms the servo. We've also made sure that in the case of failure, or if the rod breaks, snaps, or in any way is damaged, the hatch can still be opened by the rover driving into the door.
So as for the opening of the door, as you can see in this diagram, the servo will rotate the first gear, and the first gear will subsequently rotate the second gear. This will allow the rod to rotate, and this will let it unlock the latch and subsequently the door. The gear ratio is currently not finalized, but this is a general mock-up of what this design should look like.
Next, for more specifics on the door, so we have pushed back the cross membranes at the end so that the door can spread across the bottom, allowing it to have like a hinge-like motion to open. We decided to make the door out of PETG with a thickness of 0.4 inches due to some force calculations. The PETG material will be able to withstand the stress that it's given. And then within, like for the hinges of the door, we're using a female threaded hex standoff that will be embedded within the PETG, allowing it to open like a door.
So for the servo, we decided on going with kind of a generic, I think it's a Spark Fun generic Metal Gear servo. And the reason why we chose this is because it's going to be fixed position, and due to the fact that our rotation is going to be pretty within 180 degrees, satisfies our requirement on that aspect, as well as we have not done any torque calculations, but due to the fact that we are certain that the only forces experienced by the servo is going to be the weight of the rod, and this servo is more than enough to withstand that weight. Cool. And now we're kind of moving on to force analysis of the door. One of the main points of failure for the system is going to be during ejection, where we're going to experience the most amount of force. So that's during apogee, where we're separating from the rocket. And our 3 points of contact is going to be on these 3 prongs that Rover created, just so that the force is distributed across evenly through the rover. But those same interfaces are going to be the same area where the rover is going to hit against the door. And this is just kind of showing that the force is going to be compressive because we have the black powder charges experience going to be impacting door from one end, and then the other end, it's going to be the force of the rover due to acceleration. It's going to bang up against the door. Yeah. Cool. Cool. And then for calculating the actual rover, kind of just actually calculating the actual forces involved in load calculations, we decided on using basically the force that Rover provided us, which is 312 newtons, and that is the acceleration force that's the acceleration force of the rover, and we multiplied this number by a factor of 1.5, and what this told us is that what this allowed us to tell us is that the expected strain is going to be about 0.97%, which is well below the maximum strain of aluminum of 4%. And this is kind of, as well as if we just kind of just do maximum strain over expected strain, we can see that we're 4 times above we're 4 times above kind of the expected amount for the safety factor. Cool. So now on to analyzing the hinge mechanism. The 2 points of contact are going to be experiencing a similar type of force in the worst case scenario. And that would be in the case that all of the force is going to be absorbed by the hinge, by this hinge mechanism. And the main points of contact are going to be kind of the rod pad as well as the door handle. And this load calculation, our main goal for calculating is to figure out the surface area needed if we were going to make both components out of aluminum. And we figured out that the required amount of air that we need is going to be around 2.3 centimeters squared. And we can then figure out that if we have a safety factor of 1.5, it's going to be really close. So we can see that the maximum strain is going to be about 0.12, while the expected strain is going to be 0.119. And that's for the worst case scenario where the latch where the hinge mechanism absorbs the maximum amount of load. And now we can hand it over to Justin again.
2 proposed solutions under consideration in order to ease our worries about the door handle breaking is 1, increasing the amount of area experiencing force. As you can see in the image on the left, we have 2 door handles. That way we can split the force that each one experiences. And then on the image of the right, we've changed the material of the door handle to something stronger.
So for the antenna actuation, we have a clamp attached to the end of the antenna, and it's tightened by a 440 screw. And this clamp is also attached to a PETG block, which is connected to the clamp, and it also has a cutout for the servo horn. And the PETG block also has a cutout at the end for a place for the coaxial cable to go for the antenna to touch ground and the Mars board.
So one of the issues we're dealing with in our servo mechanism right now is that blue servo at the top. From the top of that to the top of the L channel needs to be roughly 0.8 centimeters based on last year's crossbeam members, the thickness of them. We're currently at 0.7 centimeters, so we're currently looking at ways to try to reduce that. So for the actual antenna system itself, we're looking at using a coaxial cable with that central inner part, providing the power to the antenna, which is the metal rod. And that the stripped silver part
would attach to the metal plate, whether by a clamp or by soldering. We're using a metal plate as a grounding plate. And the size and spacing of it now is to be determined based on future payload renditions, because we don't know where we can mount it currently. And it has a cutout in the middle for the metal rod to sit so that it can be actuated up. And we've included a spacer to ensure that the antenna doesn't touch the metal plate and doesn't short circuit. And then showing the difference between the unactuated versus when it exits the payload and actuates about 90 degrees upwards to receive a signal. We're planning on mounting it to the top of the rover. Again, we're waiting for Rover to give us actual design that we can find somewhere to actually mount it. That's to be determined. And then, as we said, all the holes and the actual shape of the metal plate, we're trying to get it to its maximum length to provide the best type of signal to the antenna itself. But all that's to be determined, and hopefully we can mount it to the top of the rover and get it to cover the whole actual rover top.
So the specific servo that we decided to go with was the SG90 Metal Gear micro servo. It's from the Missouri line, and it's known for its reliability. I think you mentioned this earlier, but the rate is around 9 grams. And the main use for the servo was to actuate the antenna from 0 degrees to 90 degrees and have enough force to keep it there. And we calculated that the required torque was about 0.026 Newton meters. We got this from our CAD modeling, so we got the volume of the antenna. And we also decided that the weight for the antenna was going to be aluminum. This is likely to be an overestimate on the weight, but it's better to have an overestimate than to have a lower. So it's better to overestimate the required torque than to underestimate it. And then from the manufacturer specifications, we got the stall torque being 0.147 Newton meters. And our available servo torque from that is 0.7 Newton meters. So it's way above than what we actually need. So those were the specifications. So do we have any questions? Yeah.
Well, without there being issues, assuming that for the order.
Yeah, I'll let Justice answer this question.
Do you want to talk about the force analysis?
Yeah, I can take this question. So, yeah, the actual friction, kind of keeping the two, keeping like the door handle. Let me just go back to that slide. Yeah. I think I passed it. Is it? Oh, sorry. There you go. Cool. Yeah, so one thing that wasn't mentioned, we forgot to mention, is that we're gonna use guiding, we're gonna use like components to probably like sorry, I forget the name, but like bearings to actually guide the rod so it kind of keeps a fixed position. And that's kind of what I plan on like keeping it so that it doesn't like move out of position, if that makes sense. So there will be like a guide that would stop it from like moving, if that answers the question.
Yes, but
yeah,
like, they're not getting some sort of internet of it. Like,
yeah,
Rover's kind of fighting that force along the work.
Mhm.
That's going to end up with your rod, right? Rod like this, and then your handle like this, and they're going to shove you in that surface area.
Okay.
Which when you try and then rotate, it's going to cause some of the friction.
I see. We haven't considered that. Yeah, we haven't considered that, but that's a good question. But unless you want to,
Yeah, so the area of interface between the rod and the door handle is pretty minimal, which means that, yes, there will be friction forces, absolutely, when it turns, but it shouldn't be anything that the servo can't handle. If that helps.
It's more towards the fact that there might be weight pushing against it. I'm guessing your issue would be like, what happens if if the rover was constantly having its weight pushed against the thing? Yeah, yeah. That's a good question. We'll probably address that later. Yeah. Mm-hmm. Yeah. Mm-hmm. Yeah. Well, if it's tilted, for example, that's why we have self-riding as well, to make it so that it's in a better position, as well as if the door is kind of already kind of leaning in like an already awkward position, it can't really open as well. So that issue is kind of, yeah. So kind of, it would be more towards like the environment kind of playing a role in kind of just stopping the whole system from actuating. Yeah.
So for the
yeah.
For like the black powder and the shit thing.
Yeah.
You also consider that the door itself, after it gets affected, will also go under like its own sort of bending just by itself, because when the parachute opens, you're gonna get like a shock and the rope's gonna kind of want to jump into the door.
Yeah.
So I'll just make sure that you account for that. You just have to like, because we know the parachute opens force, we can figure that out.
Yeah.
And like we know the mass of that, so like we can figure out how much force is gonna be pushed into the door that happens.
Yeah.
So I'll just make sure that like your gears aren't gonna slip with the servo or anything when that happens.
Okay.
Or like that latch or anything just like fall. But then it's gonna be like, obviously this rover's not gonna be that light, like it's gonna be considerable amount of force getting pushed into it. So
About like 3 pounds or yeah.
yeah, like the parachute, like it's a decent amount of force in the parachute.
Yeah.
So I would definitely make sure that once they get the parachute open force, the other still.
Yeah, we kind of, once we get more information, we'll run more calculations. Yeah.
I just, that.
So I saw the ground for.
That, yeah. One of the main like reason why we have a gear is so that we can create a more secure kind of base for the actual rod. So we don't have too much force going into the servo and kind of relying on like the threaded the threaded fitting for the actual servo horn. We're not relying on that for the actual like withstanding that force. Does that answer the question or?
Do you have a plan right now for manufacturing the rod, like specifically the handle on the end that's gonna attach, just because it's so small?
Yeah, it depends on, it is like 0.5 millimeters. So that, or actually, no, it's not that. I need to act, that was 5 millimeters was the rod. I'm thinking about the antenna radius. I'll have to confirm, but for Washburn, I'm pretty sure I have to look at actually like the minimum requirement for the lathe, because we would most likely use a lathe for this part. But if not, we would just like have it like manufactured from a different outsource manufacturing. Yeah. Yeah. I guess, yeah.
Sorry, I apologize if you said this before. I was looking at your slides earlier today, and I was curious, the antennas could be the as well. Do you know if you could safely bend it at all, or does it have to stay perfectly rigid when it needs to stay straight? Okay.
I have another question. On your one of those slide 163.
Yep.
What does the available smooth curve?
That's just representing like half of the stall torque. Oh, that's incorrect. That's incorrect. It's 0. Yeah, 0.07. My bad. Yeah.
I have a question on Payload Recovery. Maybe I'm misremembering. The payload antenna is gonna have a plate with probably.
Yeah, this is one of the things.
Okay, sure.
Yeah.
Okay.
I have a question, which is on slide number 56. You don't need to go all the way back to the base.
Okay.
You had two different examples for the door handle. One of them was to just make it a different material, a stronger material.
Mhm.
My question for you is, how does that actually, you have to consider how you're attaching it to the door, because if you just have the actual handle of the stronger material, I'm not sure it's going to be doing much, because the attachment points are still going to be simply. So
Yeah.
making sure you have some sort of plate or something back, washers, some sort.
One idea was to just like add, I feel like we would have to like do some like force analysis to see like imagine like for like different cases, like 'cause I think I don't know, like I haven't really run the calculations on like if like screwing into the plastic and then having it epoxied, if that would be enough. But that was like one idea that we had, but we can look into like also adding like washers and also just yeah, it wouldn't. Yeah. Yeah.
I'm definitely like, definitely try to have some sort of like thing, so like do the one that was like the hand and kind of out and put a plate on the other side and like attach together throughout the part, if that makes sense.
Remind it. Yeah, let me go back to.
So. Yeah, that right design, like if you were gonna record with it, which I think personally probably would work better than that one, because that could get jammed really easily, especially if it's hooked all the way. If you do that design, rather than just create like heated inserts or whatever.
Yeah.
You put one of those plates on one side and one on the other, and then it would kind of land itself down.
That's exactly what I'm saying.
I don't
So
visualize. Yeah.
it's spreading out the force, so it's not just on the screw holes or whatever you do piece and inserts into the actual material. If you put a plate on the other side, it's going to be distributing force across the whole.
Oh, like a plate that goes across it.
You've got a plate underneath the door handle right
Yeah.
there. You just do another plate on the other side.
That way it's
Okay.
not actually just going, like, instead of just relying on the piece of inserts, which I think you'll find you're not gonna be shown.
Okay. Yeah.
Especially with the ejection.
Yeah.
Cool. Yeah, we can do that.
It's
Yeah.
also like, are you?
2 arms.
Like one on each side.
One on each side for like you just have 2 different rods. We could do that. It depends on how much space we are available.
Cause that's like, so it's holding a lot, but not near the center.
Mhm.
So like,
Yeah.
if it, for whatever reason, it's somehow that it gets like a little bit on one side,
Yeah.
it's gonna be a lot of force in that rod's gonna.
Okay. Yeah. Thank you.
Yeah, this is mounted on the lander, right?
This is gonna be on the lander. Yeah.
Okay, so I wonder if you could put like a bearing support right by this mechanism at the end. And then that probably reduce any likelihood of jamming. Maybe like attaches to the L channels, does that
Yeah.
make sense?
To like kind of guide the rod. Yeah. Okay. Yeah, that makes sense.
But I guess what I'm trying to find where just like, this rod is very long.
Mhm.
And it's gonna, like, it's gonna get a lot of axial force on it.
Yeah.
I just feel a little worried that that's for this thing of a rod.
Okay.
No, I'm not even, it doesn't. I'm saying like when the ship opens, the Rover's gonna get like the board and like rod especially if it's just aluminum, could very easily just snap, like.
Okay.
Yeah. What type of calculation?
We could, like, that's just straight up, just like a cylinder being pulled up, like,
Is that just like strain, tensile?
basically.
Okay.
And like, we could test this on campus, I think. I mean, it's a little bit of a test piece, but I'm personally concerned about the door opener, because that just is a lot of force being put onto one point.
Yeah.
Not in the center.
Yeah.
So I would just definitely like look into ways to either maybe, like, even if you are stuck with this beam, it's gonna like sort of closer to the front, that rod is not, it's just such a long, narrow rod, like it's gonna want it.
I would just say like removing it, it will most likely have to be behind the rover, just due to the fact like the rover is kind of taking up the whole space. But yeah.
So this servo is staying
back. Yeah, staying in the lander, yeah.
Slide, I guess 163.
Once, what was it?
Sorry, 163. It's not.
Yeah.
Just a note, I don't think it'll be too big of a problem, but if you have, or sorry, 162. That's. If you have coax, just make sure that you have a little bit of extra length, because when the antenna rotates, the coax will have to extend a little bit.
Okay, yeah.
I don't think it'll be too big of a problem. I just wouldn't want you to like cut the coax to the right length and then when it goes to open.
It would kind of like strip.
Not quite.
Yeah.
Sorry. Bear with me for a second. This is like a big change, but it might be worth it. If you go back, this is a long way back. You go back to like 147 or 148.
140.
Either one, 8 or 7, it's both words. But
yeah, 148.
Okay, so something I just like, I'm wondering if it might be easier to retain the rover rather than retain the door, if that makes sense. So
yes,
because if I remember correctly, I mean, we'll hear about this, but the rover's chain tracks are like in material, right?
Yes.
So it should be like to move forward.
Okay, yeah, so I will be talking about that a lot. The tank tracks, I really don't want them to be a retaining device because I don't want.
I agree.
But it will be easy to fit, a secondary retaining latch would be part of the mechanism to the back of all that.
So I'm wondering if like there's some sort of thing to that, because like I agree, it shouldn't be retaining, but it will help just like friction wise.
I would say it's best if it's a redundant thing, so it's not creating axial stress during like. Actually, no, wait. Yeah, so it's not during the acceleration.
Because adding moment has no speeds.
Actually, the motors are easy enough, you can spin with your hand. So I feel like the ejection forces would be enough.
You could cut the latch with a little bit of tolerance such that during acceleration, the rope will be pressing on the door panel when it's constrained. But during the parachute sequence that you're talking about, if like that front thing completely snaps off, the door's hanging open, then it falls down, 0.5 millimeter, and then it's resting on that secondary latch.
Yeah, so what I'm thinking is like maybe you have some sort of motor, some extra component near the front of the door, rather than holding the door in, it's just there to. So like,
okay,
something that flips down, Rover's butted up against it, you flip that up, and they can, so like that way, if something does happen, you have that, because like that is also gonna be much like the moment on those will be so small because they're so tiny, and like kind of be.
I thought you were talking about holding the rover.
Yeah, I was also thinking from the back. Yeah.
Like just some other way that's like, because that rod is just asking to see.
Okay.
I would see if you can retain the rover itself rather than the door.
Yeah, it's in our back rod, so by the drive, it's like the back plate and motor plate would easily fit so the latch like second thing.
Even if it's like secondary.
Yeah, I think that's good for especially like redundancy, but yeah. That's kind of that's also an idea that we had, but we were kind of concerned about the space behind, kind of the space between the rover and EMP and stuff, right? But we can get to that. We can definitely talk about integration. Yeah.
Sure. Yeah, in front of the slide.
Oh, okay.
Sandwich cells with screen and stand long enough forward that your legs hit the table.
Yeah. They don't see what else. That way they just. We have one to play. Yeah. It's like that. It didn't want to acquire. You want
to be in our photos? You're gonna put up.
Right hand. With my hand.
My computer's going away in my. That's actually in the presentation.
Y'all remember, yeah, you're first, and then. Yeah. There's speaker notes will show up by next slides. Yeah, what's it, order? Cool. Awesome. Awesome. I heard the gain is, okay, it is really loud. Hi, all right, welcome to Rover Structures PDR. To start off, I was gonna give a quick overview of Rover mission. I think there's been like 2 payload PDRs though, so I will very, very quickly speed through it. We're gonna deploy from the protective lander craft after self-righting. Our goal is to be able to drive on the sandy, potentially bumpy, unpredictable terrain of the desert landing site in Pecos, Texas. The rover will be able to communicate with ground station through our deployable antenna, and ideally we will get to do 2-way communication and send live video feedback. And then finally, ground station operators and other HPRC members will be able to remotely navigate the rover craft across the terrain to an ideal recovery point, and ideally we could potentially drive all the way back to ground station, launch site. To give a quick, we're about to go into several subsystems from a large 1,000-foot view. I think this is actually 1 foot away, but the rover is built off of a central frame of 3 rods. You can see them 1, 2, 3 over there. And then the batteries are mounted in the center above the rods with our open MV cam and mainly ultrasonic sensors mounted in the front, drivetrain motors mounted in the back with the screws below the frame and the motors above the frame. And finally, the screws fit into specifically made 3D printed groove pieces that are attached to the L channels to allow the rover to leave. In the larger payload, the quick reminder, the rover will be facing downwards during launch. So the accelerational forces will be from the actuation panel, will be pressing up against the front part of the rover's frame. Here you can see in green is the outlined actuation space. That's what the current setup. As we do more optimization, where more space is needed, we can definitely fit some more. That's just based on current models. And then self-righting would sit above in this case. So starting off with mechanical, for the frame, we are expecting, based on Rocket's early simulations, 312 newtons of acceleration force. As you can see, that's axial from the front of the rover because we're facing downwards, and that's with the 1.5 times factor of safety. 3 central rods of the frame will handle the acceleration forces, and the goal of this is A, not to have the rover collapse, B, to transfer all of these forces away from sensitive components like the sensors, motors, and especially the screws and drivetrain so that they could get misaligned from these forces. The current plan is to vertically printed with PETG to provide maximum strength for the additive manufacturing. And we can potentially also add central metal rods if needed. Here it's shown as one combined part, but a lot of the top mounting pieces may be additionally made with screws on in the final model for easier assembly. Here's the cross-sectional profile of the rods. We did a strain analysis, assuming we don't want the rods to deform more than 1/5 of a millimeter.
basically setting a very, very high or very small threshold that we know it's not going to mess up the drivetrain or anything like that. If we set that as our max deformation, using experimental from a paper, their data on the elastic modulus of PETG, we found that we need a 50% infill, 3.28 square centimeters of area for the cross-sectional profile of the rods. Our current design exceeds that with 4.456 square centimeters. And if needed, we could also add, instead of the red profile area, we could add metal shafts to constrain it and add additional supports.
All right, so I'm going to talk about the drivetrain. During the beginning of the year, we talked about several different propulsion methods, and we ended up going with screws instead of wheels or tracks. The reason we chose screws was that they have very good traction. They have a high surface contact area, more so than wheels, especially if one or more wheels were to get lifted off the ground while going over rough terrain. And they're a lot simpler than tracks. There's less parts to break that could break. So hopefully it would lead to more overall reliability. For powering the screws, we chose between several options and ended up deciding on belts. We decided belts because we believe them to be the best at dealing with dirt and sand getting into the system and clogging things up, or ideally that not happening. So belts face inward, unlike gears, which face outward, which means they would be naturally more exposed to the environment. And belts don't require lubricant, which could attract and have dust, sand, and or dirt stick to them. Just move this, I can see my hands. We believe that belts may be a bit less likely to become dislodged during launch from vibrations than gears. And we decided that direct drive isn't a good option because it either increases the overall length of the rover or decreases the screw length. And the motors being close to the ground is very bad for dirt and sand and other stuff getting in. All right, so quick overview of the drivetrain dimensions. We have a gear ratio of 1:1. That's on the pulleys. That doesn't include the built-in motor gearbox. We use a 40-tooth, 3mm HDTD timing belt that goes to two 16-tooth pulleys. And we use our total height, which is 7.14 centimeters, is the max height used for the drivetrain section of the rover. And the screw outer diameter is 2.8 centimeters. Okay, a few notes on drivetrain mounting. For the motors, they screw into this back plate here, which is partially transparent. Obviously, won't be that in real life. Sorry, my bad. Misspoke. They screw into this plate for secure mounting. Each of them has 4 mounting holes. We can use all of them. And then the motor shafts are supported by this partially transparent plate here, so that the motor shafts are not cantilevered. The hex shafts, which drive the screws, are also supported by this back plate, so they're not cantilevered at all. And we will have bearings for all plates for that the hex shaft goes through. They're just not shown in CAD right now.
Okay, so going into the screw design. So when we first started researching what we wanted to do with the screws, we looked at a paper published through IEEE to help determine what the ideal screw parameters would be. The paper provided some nice values. So they talked about the ideal outer diameter and inner diameter dimensions, which are 88 millimeters and 77.5 millimeters, the ideal pitch angle, as well as the ideal pitch for the screws. Moving forward, we're planning to test 2 different outer diameter to inner diameter ratio types, both the absolute difference between the inner diameter and outer diameter that the paper provided, which is, I believe, 10.5 millimeters, and then also the relative difference. So just taking that ratio and then condensing it down to fit within our rover dimensions. And in order to drive the screws, we're planning to use hex shaft, which is going to transfer torque, and then also mount them to the rest of the rover. So moving on to the screws L-channel mounting. So we plan to have L-channel that's going to be, or mounting to the L-channel, we're going to have 3D printed mounts. These mounts are going to have grooves that are going to match the profile of the screws. So in order for the rover to actually leave the lander, it's going to drive, push up those grooves, exit the craft. We're also planning to have a large tolerance in these grooves, so that way during the rocket's flight path, there's not going to be any damage to the screws.
So now we're going to move on to the electrical system of our rover. We're going to talk about our minimum speed and torque requirements and why we picked our specific motor. So obviously Texas is flat, so there shouldn't be many hills, but to get to the baseline for the max torque, we're supposing that there's a 10-degree incline slope. And so we use this free body diagram analysis of the force of gravity on the rover, and we use it to calculate the force of thrust of 2.317 newtons to maintain a constant velocity. And from there, we use the paper from IEEE on screw propulsion and use their experimental data to show that to achieve a 2.3 Newton force, we'll need 1 Newton meter of torque as shown in the graph. So to do this, we decided to go with the Dartbox V2, So using this graph, we know we want a thrust of 2.3 Newtons, and we're assuming that since we have 2 motors, we'll have to use smaller screws, and we don't want to go below 10 centimeters per second. So to obtain this value, we use this formula, which says that the rotational speed equals the linear velocity times 2 pi over the pitch, and then we converted it to RPM. So to recap, our minimum requirement torque is 1 Newton meter, and our minimum rotational speed is 150 RPM. So to do this, we use the Dartbox V2 HR motors, and they're from Just Cause Robotics, and we use them because they operate at 300 RPM at 12 volts, and they also have a stall torque of 2.686 Newton meters at 10 amps. This is a brushed DC motor, which gives us a good balance between torque and control. And the stall current exceeds 12 amps, so our electronic speed controller needs to handle peaks above that level, also without overheating. Other specs about the motor are that it weighs 60 grams and it measures 50 by 22 by 22 millimeters. So when first choosing how to control our motor, we had to pick between using speed control and position control. And we did eventually decide to go with speed control because our rover's drive system needs continuous rotation and also high speed ability and not precise angular positioning. So positional control is great for robotic arms, but it also adds unnecessary sensors and complexity. And since we care more about maintaining a constant speed and responsiveness, speed control was the clear choice. To drive these motors, we selected the WASP ESC from Robot Power. And this controller is compact and lightweight, weighing only 9 grams. And it helps to keep the rover's overall weight pretty low. And despite its small size, it's capable of 10 amps of continuous current and up to 30 amps peak, which gives us enough overhead to handle the motor's stall current without any risk of damage. The voltage range is also between 6.5 to 28 volts, providing flexibility for different types of battery configurations, even though we'll still be running it at 12 volts to match the motors.
All right, now that we have our motor and ESC selected, we wanted to look at the performance of our rover. We considering 1 Newton meter travel torque and an efficiency of 0.85, and using 4 lipo cell batteries, each with 3 milliamp hours, we have a total battery life of 12 amp hours. So going off of that, we came up with this spreadsheet to calculate our motor performance. Looking at some of those key results, we expect 7.673 amps, that's including the antenna, and a time of operation of 93 minutes, 0.84, and a total range of 1.22 kilometers or 0.758 miles. The image on the right shows our launch, shows last year's launch site and last year's touchdown with an overlay of our expected range with these parameters. Now we'll move on to the sensors. One key theme of our sensors is we wanted to make sure our rover could operate safely. The NTC thermistor does this by ensuring that our motors don't overheat during operation. They have a range of -55 degrees Celsius to 155 degrees Celsius, and they'll be placed on each motor, 2 of them, to ensure that the motor doesn't overheat during operation. Outside of that, we also have a motor current sensor. This compact sensor can measure voltage, can handle voltage from 36 volts DC to 15 amps continuously. And again, this is to make sure that our motors don't exceed an expected current. Outside of that, we have ultrasonic sensors. We're going to have 3 of them on the rover, 1 on the left, 1 on the right, and then 1 right in front. These have an operating temperature of -15 to 60 degrees Celsius, They can sense 28 to 450 centimeters, and they have a sensing angle of 44 degrees. We went with these sensors over infrared sensors, which by comparison are much smaller, because we thought that these sensors would theoretically have better performance in the sandy environments we expect. This sensor is also waterproof and designed for outdoor environments. And finally, we have the Open MV camera sensor. It contains built-in compression, 70 to 115 degree field of view, dependent on the lens. And then it's also quite compact for its size.
Now we're going to go over the software for the rover. So here's the state machine that we're going to be designing and modeling the code for the rover. So here's a high-level overview of the code. First, in the rocket itself, we're going to initialize the robot. And if the IMU detects that we have landed, then the rocket's going to go into self-righting phase. And then once self-righting is complete, the panel is going to open. And once the panel opens, we're going to have an automated drive out for a fixed distance. Once we've driven for a certain distance or time, the antenna is going to deploy, and we're going to have a checker that once the antenna is deployed, we're going to go into a state called the waiting for connection state. Now, this leads us into our lower level modes of either the ROV mode or the autonomous mode. Now, in the ROV mode or the remote operated vehicle mode, we're going to have basically a data flowchart, and this is going to be the phase or the mode that we actually want to be in, where we can control the rover with a controller from ground station. So we're going to go from that waiting for connection state, and if we do get a connection, we're going to go into the state. We're always going to have a state checker that you can see in the bottom, that if we lose connection at any time is going to take us from the ROV state into the autonomous state, which I'll be getting into in the next slide. Now, how this state's data flowchart works is we're going to have a sensor processing block that takes in sensor inputs of the OpenMB camera, the current sensors for the ESC, the IMU, the temp sensors for motors, the 3 ultrasonic sensors, and the GPS data. That's going to take us into encoding, and then that will lead into antenna. And antenna is going to pass information between ground station and itself, and will also pass information to command processing, which will send a PWM signal from our controller inputs. Next, we're going to go into the state machine for the autonomous state if we lose connection. And again, we have that same state checker interrupt at the top. If we lose connection, we're going to go into the, or if we regain connection, we're going to go back in the ROV state. And we're going to come from the waiting for connection state. And if we're unable to connect to ground station, we're going to enter autonomous driving. If we detect an obstacle, we're going to go into idle and then begin reversing. If we still detect that object in front of us, we're going to keep reversing until we have a set threshold distance that we want to reach. If no obstacles are detected on the sides, we want to enter a object avoidance state. We're going to test different modes for that, and we'll have a more concrete plan for that later, but basically it'll allow us to go around the obstacle. And then if no obstacle is detected in the front, we're going to go back into autonomous, and it's just a loop. And once we get that signal back, we will go back into the ROV state.
Awesome. Here's our to the papers we cited are linked here. So questions? Yes.
So I'm reading word for word. This is not.
Oh God. Okay.
Why did you select an ultrasonic sensor for detecting bushes? Ultrasonic sensors have difficulty with porous objects, and I don't believe it would work. Camera vision is likely your only option. Obviously, heating and power will be major issues. The algorithms were partially developed in 2023 and 2024.
For the camera vision? If we can get camera vision running, we'd absolutely be open to using it this year. We went with ultrasonics because, as far as I know, infrared is worse. But if I know our R&D is looking into that right now, so if they start getting data back that IR would be better, we could absolutely switch course. I mean, they're easier to integrate. And again, camera vision would be really cool, but that's a large task that the ultrasonics are mainly here as a nice backup that if we can't get live video feed working, something was wrong with the camera at the last minute, we have it. And as far as I know, my impression was as far as the very simple like scalar distance sensors go, I think I know what you're talking about in terms of like, yeah, for like porous objects like that, yeah, it's gonna have issues. But my thought is that we'd still get something compared to like a single spec IR.
Do you know?
Yeah. If we have pre-written code, we could always put on the OpenMV. It's the same camera.
Yeah, there were algorithms for the OpenMV to detect bushes.
Cool.
This is kind of looking from above, but I'm sure the same concepts still apply. And I also know the person who wrote that code would be thrilled if it was using it. So
cool. We could look into integrating that. Yeah.
Questions for other people? No questions for other people. Oh, what? You consider radar?
No. That was not on our initial. My understanding was also size of whatever that would be difficult. But if there's
theory radar, I'm radar.
for the purposes of make sure all questions get answered, I would say I want to talk to you guys later about that. But yeah, we're definitely open to it.
For this, what are the screws being made out of? Are you gonna have to-
Yes. Yeah. The current plan for.
You don't have to go back that. I don't know what that was like. Sorry. Oh, okay, actually, you should go back there.
Yeah.
Yeah, we're planning on 3D printing vertically, probably at a PETG. If that doesn't end up working, we could do like resin or something if they don't print right.
Braking or for heat?
Make sure both. I like.
Because we're thinking polycarb is like the backup, but it'd be difficult to print. Oh, okay.
Because I'm just a little worried, especially if.
Breaking from what forces?
I just like the door stuff, and like now that I know how that works, I'm just a little more.
Okay. Miko, so if that ends up being necessary, yeah, we totally. I mean, it makes it more complicated for everything if we could compare to. The whole purpose of the frame and the way the grooves are designed is really all about here. If you can see, like making sure that in no point are the screws ever under that acceleration load or ejection load. They should really only have to deal with their own weight in terms of acceleration, never any of the other rovers' weight. So let's see the photo. So the tolerances on these, they kind of look tight in here, but the screws should never, like during flight, actually be touching with their threads to those screws. They should never be taking any force through that. We can make them wider if needed, but.
I just keep that in mind.
Okay, yeah.
Especially because the actual treads of it are gonna have to pass the words it looks like. So, because they're a bit too much at an angle.
Yes, yeah.
Not a lot of material holding them up at like the very edges of them. And like that might just start peeling off, because I've had issue with that.
Okay, yeah. You see, you're worried about the outer parts of the thread, not the.
I'm not really worried about it.
Okay.
I'm more worried about like the actual thread themselves, especially like.
Interesting. Yeah.
Just very thin.
Yeah, they will be kind of, oh no, we'll look more into that. There might be ways we could just reinforce the threads maybe specifically then and not have to.
Yeah.
Because if we're custom ordering a part, then that just makes it more complicated for like replacing or changing them. So, yeah.
If you go back to slide 170.
Yes.
So maybe this is the perspective. So will there be any space like above the Mars board? Like in this
Okay, yeah, so the Mars board, the current plan, last time me and Steve talked about is that in order to mount the antenna, like actuation servo, it's not on this CAD yet, because I thought that including too much in covering would make it hard for people to see, is that the Mars board is going to fit in a slot, basically, with some kind of room to fit whatever cables needed. So that'll be basically defined by how much space the Mars board needs vertically. Okay. But then it's going to fit in there, and then antenna will be putting that servo and mounting above it.
Okay, because my other concern is for the radio on the Mars board, there is like, it's almost like a stand, like the current designs there are like standoffs.
Does that have to be attached to the Mars board?
Okay,
it does.
Well, I mean, theoretically.
Is there's a way we could, I didn't see that on the CAD, so that's why it's not accounted for, but. Yeah. What's that? Yeah.
Yeah, because I think that,
But just, yeah, maybe,
okay.
Maybe that wasn't communicated, and that's like.
I was pulling from the full CAD files from last year, which I didn't see anything else sticking larger than what's accounted for in here.
Yeah, because the board, I guess, maybe there are two different groups. But yeah, the idea is the radio board separate, and the current design has it like on standoffs above the board.
Yeah.
And so but that doesn't fit, which again, isn't necessarily your.
Yeah, would it be possible, to have the board be separate and just wire connected, so it's not on standoffs?
That was my thought.
Okay, that would be significantly better for this design. Cool. Yeah, Owen.
Yeah, so I love the whatever green bits that threads fit into. When it drives out.
Yes.
There needs to be something constraining it from the other side. So otherwise it'll just drive straight up first.
Straight up.
So if you go to slide like 180.
Yeah, sure. Sorry, I'm a little confused by that.
So the way you have it now would work if they captured like more than 90 degrees of the thread. But since they don't, I believe it'll also be pushing the rover upwards. Right out.
Maybe. I don't think so. Are you worried that it would create a pressure where it creates friction so it can't drive out?
No, but so I guess gravity would hold it in.
We can have the grooves encompass more of the screws if needed. But yeah, that's definitely feasible. We'll have to work around cross members.
Question from ladies.
Yeah.
What's on the payload going like this in the bullets coming down of their parachute?
Going like
just rattling around. Yeah.
That's a good question. From
nothing's on top of it, right? Pulling it down.
Nothing is modeled yet on top of it, but we can put. We'll definitely want to put a clamp that pushes it the other way from self-righting. Yeah.
That was my only. That parachute comes out, that rover is going to be rattling around.
Yeah, no. I mean, so it's I don't want the constraint to be those grooves. Those grooves should have a high tolerance and not be getting scraped up and damaged by the rattling. Okay. But the lack of rattling, because it's not going to be rattling. But so from the bottom, it's constrained with those frontal rods, and we can have either those rods or something else extended on the top. That's just a question of working out with self-righting and actuation, because I didn't want to put more stuff in that space that they need.
I just want to make sure that gets.
Yeah. No, that's.
That could theoretically, if it were not trained, just so we're all aware, that could tip the rocket. So.
Okay. Oh, so you need especially on the way up. Yeah.
Yeah. You can't have things vibrating like that, especially that heavy mass at the top. So.
Yeah. So we should be. The rover's at max width, by the way. So it'll be tightly pressed up against the cross members as well.
Okay.
But yeah. Cool.
Thanks.
Are there any more from the thing?
Yeah, well.
There's more.
Okay. Yeah. Cool. Thank you.
Just go to your slides.
Yeah. I may have slightly misremembered the dress code, but I'm taking that as a good thing.
What changes have you done this?
Slides, I broke down this. That's cool.
We'll just keep it how I. Yeah. Sorry. We're gonna stand up here for a second.
I'm just saying, right?
What do you think about the line?
We should probably.
Yeah, I'm an 8 with the overload.
This isn't gonna work for bottom, I'm not expecting, like.
Okay, just like something to be like, that's not an important.
Yeah.
You guys can start whenever.
All right. Is this a good volume? I have no idea how sensitive. All right, perfect. Yeah, this is 30K Composites PDR. So to start, as a little overview of what Composites is in charge of. Composites does all the sort of cutting and squaring of the airframes and just coupler tubes, nose cone, shoulder, all that. The fiberglass tubing that we use for the rocket. That isn't something that's super like design heavy. That's something that's pretty standard each year. So that isn't really going to be gone over in PDR in future slides. But also tail cone manufacturing, which is something that we did not do last year. Our tail cone this year is going to be an OGAB shape, as that helps with integration with structures. It gives them a little bit more room to work with before the slope gets too steep. And it is a better shape for drag. And then we work with the fins. So there's 3 fins obviously on the rocket this year. So they're going to have an airflow cross section, and we are in charge of creating a jig to bevel the fins to have that perfect cross section that we want, as well as manufacturing the fin can, which involves the fillets with the fins and the fiberglass slabs. Right. And that's just a model of the fin can there. All right. So for the timeline with A term, we did a little overview about what Composites is. A lot of the members on this sub-team are freshmen, so it was kind of like an onboarding thing. And then we started with our design process. So the bevel jig, base plate, which I did not mention in the previous slide, but we'll go over in the following one. The bevel jig, the base plate, tail cone mold, all got designed during A term. And then we also began, as in that photograph, practicing with fillet procedure, because a lot towards the sort of second semester of the year of Composite switches from being like design heavy and more actually working with integration, or rather assembling the fin can. So it's important to get those procedures down ahead of time as early as possible, so that when the time comes, we know how to do it. So yeah, for B term, the current plan is for prototyping and eventually developing final designs by the time CDR comes around, and then continuing with those practices so that we sort of iron out any of the issues that we've been having, which will get gone over later on in the presentation. And then manufacturing and testing coupons, which is also something that will come up later. And then for future plans for C term, ideally we finish manufacturing the final designs for that base plate, bevel jig, and tail cone mold. This is when we would be squaring tubes, when we would be doing the bevels and the fillets and all that, and actually manufacturing the tail cone with the mold. And then along with that is just assembling the fin can. Some of that may end up carrying over into D term, which is fine as long as it's kind of early in D term. We have the time for a little bit of that work to carry over. But other than that, yeah, final integration of Rocket, and then eventually Composites is in charge of painting. So yeah, we'll move on to the base plate. Okay. Okay. So the objective of the base plate is basically it's used to attach the fins so that they're normal to the body tubing. So last year's base plate only had one section in which the fin could be attached to. So the new design that we have for this year is that it would have 3 sites for the fins to be attached to, and this would make it so that when you put the body tubing and the 3 fins together, you can't really move the rocket, or you can like spin it, and this would help prevent any like translational or rotational errors in the fins, and also would help prevent canting of the fins.
So with the bevel, we, as opposed to some of last year's stuff, which we'll get to shortly, we wanted to design and manufacture a jig that could consistently give us good reading, or give us a good, give us consistent fins, basically 3 identical fins. And we have to sand each fin repeatedly, and 3 sides of it, and sand each fin on 3 sides within a pretty tight tolerance. And yeah.
On the screen right now is what we had for last year's design. The main problem with this is that it was entirely hand sanded, and we weren't allowed to use the machine sander. This meant that it took a very long time, and we were very prone to human error. We want to redesign this and find something that A, utilizes the machine sander that we have, and will be much less likely that human error plays a factor in this. As I said before, this design really did not work too well last year. So what we have next is our future designs.
So our first idea, the idea that we fleshed out, or the idea that we fleshed out the strongest, that we did the most CAD modeling for, because this is currently what we're planning on sticking to, or something very, very similar to this, involves the sanding belt that we now have in Sagamore. So I believe this model actually is made a little bit thinner, that is actually like wide enough on the sides to do this, but just extruding those little side bits more would get this to work. But it would be able to slide back and forth along the sanding belt, so that you're not putting the same part of the sanding belt along the same part of the fin, in case there's any sort of like, obviously the sandpaper is going to wear down eventually, and that's not going to be perfectly even. So we're not getting any sort of warping from that, because we're able to slide it back and forth. In the following slide, there's a few more pictures. So you'll be able to see that the fin is aligned with an extra sort of piece. There's some screw holes at the bottom there that you can see, that would put just a little extra piece on, that when the fin is clamped to that angled surface, it would bump up against an extra piece, and it will always land, the edge that we're sanding will always land in the exact same place every single time. And then that piece comes off after the fact, so that it's not something that can potentially get sanded itself when we are using this bevel jig, so that it doesn't sort of change the dimensions of that. Yeah, I think it's the same bullet twice there. But one issue with this design, you can see in the 2 sort of models up top, the way that, and I'll move on to the next slide so you can kind of see what I'm talking about a little bit better, actually. But the way in which this bevel jig works, you can see on the left there, or yeah, it's the left for you guys too. You can see on the left there how that fin is clamped into place, and then that little bit at the bottom will be removed. And there is that green bit right up there that you can see, the sander attachment that is also clamped to the sanding belt, and that kind of fits into the gap that is at the bottom of the main component, the sanding jig, the sliding component, so that the component always goes the same depth into, or the same distance into the sanding belt, and then is forcefully stopped so that it does not go further in, and we always get the same exact bevel depth, which along with that, given that it's a consistent angle, would give us the same bevel angle as well. One potential issue with this is that if the sandpaper kind of wears down, that is technically a slight change in thickness that will technically affect kind of the bevel deck there. That is something that in the future we could maybe redesign on so that that would not be an issue. But as of yet, that is kind of the main issue with this design. And the translucent bit, translucent sort of rectangle there is just showing that the table that we're doing this on is taken into account in terms of physically being able to clamp the pieces where they would go. Because that was an issue in last year's design, is physically being able to fit clamps where we wanted them to. So taking that into account. Yeah, I believe that's all for this. A slight variation on this design that we had was with a track. This would kind of avoid the human error of accidentally tilting the jig in a way that would create kind of a weird bevel on the fin that you don't want. In the previous design, you could tilt it a little bit and be fine, but if you accidentally create like a crazy like angle where it's not kind of in plane with the belt sander, there's a possibility of nicking the fin in a way that you do not want to do. This design would avoid that, and it would avoid any kind of human error involved in not having the jig perfectly aligned with the sanding belt. However, the issue with this is, one, our fins are simply too long to be able to go the short ways with the sanding belt. It is 4 inches wide, so we would have to somehow rotate, have that align with the sanding belt when we're going the long ways with it, which is just an awkward thing kind of to set up, and that's a little bit of a design limitation there. As well as that is the current kind of way we thought this out does not give us the possibility to slide it back and forth along that belt sander. So that kind of creates an issue where all the fin is being sanded at once, and any sort of variation in kind of the wear of the sanding belt would create an issue for us with getting kind of a work surface for our fin. All right.
On the screen is the design matrix that we ended up having. It compared the trackless model with the tracked model, and each of the categories is judged out of 0 to 5. We have simplicity, precision and accuracy, manufacturability, ease of setup, and our total, which is out of 20. The trackless ended up winning out, and given that it was a bit more simple and it was much easier to, it was much more easy to manufacture. The tracks just seemed to add a bit more weight and were a little bit redundant in a lot of places. Good.
All right, so for our tail cone, myself and Robert were tasked with designing it. And for the club this year, we are manufacturing our own tail cone, which we have not done in a few years. So my job and Robert's job was to design a mold to perform fiberglass layups so that we can manufacture this tail cone. And to do so, we researched previous year's designs, so either an ogive or a conical tail cone. And we created CAD designs with new dimensions and designed a multi-part mold. So we actually used a 6-step mold, which you'll see in a couple slides. And the dimensions for our ogive tail cone. So for the aft section, we have a diameter of 1.97 inches. And for the forward, we have a diameter of 2.58 inches. And again, like Jason said, we are going with the ogive tail cone because it reduces drag, and then that's also going to improve our fuel efficiency, so we will not have to use as much to maintain the same speed.
So just to kind of go through the process here. So the process is taken from a couple years back. They experimented with various things and came to the best thing was using a vacuum sealed bag. So the way that we would kind of went about this was catting out the actual tail cone shape and then the mold. Would 3D print the tail cone mold and then use the layups inside the vacuum bag. Post-processing would pretty much just be removing the excess material. I have a photo of here from 2023 when they were initially using the vacuum seal. And then I also have a photo of the 2-piece mold just to kind of show how it would be taken apart. Now, that being said, we're using a 6-piece mold for easier post-processing. That way, we're able to take off the top and bottom so that we can easily remove excess without it really hurting the actual tail cone itself. There is the smooth design with everything kind of filleted to make sure that we don't puncture the actual vacuum sealed bag. And one thing that we do have to keep in mind, that's not catted on here exactly, but we do have those little green pegs there are bolts to allow for easier removal of kind of everything, allow everything to be secured. We will have to use some type of wax or other type of like sticky tape or some type of substance that epoxy does not actually contact the bolts and make it almost impossible to get out, because that would really not be too fun. That's pretty much it for this design per se. This is just a quick little render of what that would look like, because, yeah.
All right, as a final bit, this is more stuff that is pretty consistent over the years with the composites, but just going over the process very quickly once over. The stuff that we'll be doing in C and early D term, in terms of fin can manufacturing procedures for that, and the stuff that we're practicing right now. So we did do one round of trying to do fillets. So we'll be using a 1-inch fillet, 1-inch radius fillet sear, which provides strength on touching the fins, and that nice slope to it makes it so the fiberglass layups in that kind of mesh don't have any like stress, strain, compressive, or like tensile forces, which are an issue if we had like a right angle. But that's fairly standard again for this kind of thing. So yeah, we'll be trying out the, again, standard layups that we do, which are fiberglass meshes layered 90 degrees, 45 degrees, and 90 degrees. And that variation in angle allows for kind of combating each other's weaknesses so that there's no direction that the forces are especially weakened. Yeah, I'm not going to go over a single bullet because it's kind of how this usually works. This next slide is a little bit vague. This is not something we particularly started on yet, but in terms of coupon manufacturing, that's something we want to try out this year. So coupons are little rectangular kind of samples of the fiberglass layup. And manufacturing coupons and strength testing them with a 3-point test and a tensile test allows us to get some data to make sure that the coupons that we're manufacturing are actually able to, if we plug this into a model with fin can in a program like Abacus or ANSYS, would basically allow us to make sure that the layups that we're manufacturing are actually going to survive, essentially. And yeah, that would also potentially, if we did find a reason to change sort of the orientation or the amount of layers of fiberglass that we do with these layups, that would be the thing that would tell us that. And yeah, we did one practice, like I said, with fin can fillets. And this is basically just a lessons learned slide, which I'm not going to go over in full. But that's just to say, we are actively working on making sure that we know which parts of the procedures are especially finicky, and getting down sort of some of the art of composites. All right. That is all.
Oh, yes.
Oh boy.
I just have a manufacturing question for slide 2 and 6.
206. That's.
Yeah,
Give me 1 minute. Yes.
so last year's design, the reason that there's a little circle in there is so in order to get the 90-degree angle, you have to dog bone it.
Yeah, that was simply forgotten about in the moment. That would, I'm sorry, you keep talking.
Are those also 90-degree angles, or are those at another angle? At the top one, that I can tell that's 90, but the two.
They are. Yes.
So you're just gonna go.
Yeah, that I was realized after the fact, but was not worth going back in, and it would not fundamentally change the design. Even if we had to make those rounded sections like squared, that would not fundamentally change how this design works. So it would not pose an issue.
I assume you guys are planning to bring that in.
Yes.
Yeah, make sure you get that and the layups so that we had at the practice and so
I did see what happened to our layups. Yeah, the intention is to have kind of a double layered vacuum bag for the tailcone mold.
Sorry, I misheard you. You said last year you couldn't use the belt sander.
I think it was more we did not have one in Sagamore. Yeah, it got, I believe, purchased within the first few weeks of the summer.
Because we got lazy.
I appreciate it. Better now than never. Yes.
You go back to the slide with the base plate.
Slide with the base plate, absolutely.
So if I'm assuming that this works similar to how previous designs work, I had a question about potential tolerance stack up here. That base plate is going to be sitting on a flat surface where your angle block also would be for attaching your fin.
would it not be better to remove this kind of platform that your airframe would sit on and have the airframe kind of sit in a hole that goes directly up against your base plate in order to avoid whatever additional stack up you have?
And then there would be, instead of, there would be like gaps for the fins to fit in, is what you're saying?
Yes.
That is something definitely worth looking into.
Moves around your airframe.
All the pins.
How about instead of cutting a hole all the way down to your base, like if you can machine a flat surface, you can machine a flat surface, you could also just have it be an indent instead of and this was to a platform, because then it's still connecting all of everything.
If we cut it up, I think John's side would be much worse.
It's worth investigating. Though.
This is hard for me, I think, to picture in my mind right now, but if I even could get just like a hand drawing, that would probably clear things up.
Where the circle is, just put a dent, that's the thing, too, so
Yeah.
it's not farther.
Okay, yeah, and I see what you mean with it not being held together unless you did like an outer thingamajig. Yeah,
The pins are wider than.
Although the fins do slope a lot more than previous years as well. So they would clear probably the stock before it would go too far out though. I can see it working without needing like a hugely long thing. Because again, the fins clear kind of ridiculously fast compared to last year. Just the height of any stock we'd use with their angle.
So my next thing, you can go to the bevel jig design, the first one.
Sure thing.
So
this slide or this side?
Either works.
I will keep this
one. Question is mostly
sure.
So in the past, we've seen that this belt likes to move side by side as well as in the correct it's supposed to. That's more so a defect of it being a very cheap machine. Do you have any way to account for that? Because that will shift the belt and also kind of bow the belt as well when you start pushing into it.
That is something noted. That is something I think I am going to make a point to see for myself. Kind of just toy around with it, probably. I do see what you mean. And that was not taken into account previously. Which is definitely important, but that is definitely something that will be taken into account. And I'm going to make a point to make a trip to Sagamore and make sure I know exactly kind of what you're talking about and to what degree it does those things and whether it can be physically kind of restrained.
I have multiple questions. If anyone else needs. Okay. Also on the topic of the belt, have you guys considered moving to a finer grit belt or more precise belt? It'll take longer. However, you won't have as much of the larger your particles are, you'll have more inconsistent belts.
Yeah.
If you get it down to the smallest possible grits, it'll wear your belt faster, but you might get better result.
That is probably something that can be easily trial and errored if we just for example, a laser cut a fin while testing out our bevel jig. That is probably something definitely worth. That seems like it's a very easy thing to test out, so that can definitely be done. Just when we're prototyping your bevel jig. Does not seem like a hassle.
You have more, Noah?
I do. So my next question was the telephone role.
All right, that was this way, I believe. Yes.
So as the person who is working mostly on this in the past year, so I had a few things I want to ask you about. So in the past, these molds were printed and manufactured that way, and we did use an internal vacuum bag type strategy so that you don't have that kind of collapse that we had in the previous practice. However, we did still see the 3D print itself or even under that material. Have you considered other materials in a 3D print so that you don't get this kind of collapse on material or having 100% infill?
Can you repeat that last little half a sentence?
most of these 3D prints, even under the vacuum, right, because it's a regular shape, and your vacuum kind of like engulfs the entire thing, it still likes to warp it, even though like you might have an internal and external vacuum.
Okay.
Might get regular dimensions.
A bulkier mold would fix that, I assume.
That as well as potentially other materials.
Yeah. Okay. Yeah.
Okay.
No, I was more thinking out loud, so.
Okay. I'm gonna cut you off. Do keep asking questions, just put them in the form.
Yeah, we're saying.
Just, if you put them in the form, that's be done. That'd be great. Okay. Anyone else have questions? Okay, great. Matt, go.
Okay, if you go to the tail counts design and.
Just this?
Yeah, where are those dimensions?
I will be honest,
Are they supposed to be, are those radiuses by any chance?
yeah, I'm being told yes.
It's that.
Okay. Yeah, I did not personally input those.
Very good, I just want to make sure. And then for the the bin dig, you don't have to go back there, I just want to make sure.
Yeah.
Do you guys think calculate the from the bin when you were putting those lines somewhere, or do you just have the space and even parts?
I am gonna go back because I'm not quite sure what you're talking about.
The like, alignment based.
Oh, yes, no, that is taken into account. Those are, yeah, that's a little bit offset. I don't think it's the bin. Yes.
Okay, and then, also with this, so the reason why we only have one on the previous here, so we usually draw the lines on the body tube in the way the washroom.
Yeah.
We only have a new one. I think it's fine to do all three, but like, we still would probably need to draw the lines on it.
Yeah.
to work with requirements, so it might not be necessary to have to be able to do all three. Because like, I think we'll only ever be able to do one at a time, just to provide some of the stuff we're doing with it, like the ramps and stuff, so.
Even if we do one at a time, if you put one fin on, even if you picked it up off of this base plate and you put it back down in like a different orientation, the idea was that you could not put it on slightly incorrectly and have it still like fit was the idea. And even with the line, there's potential for human error. That is banking on the fact that this is not manufactured with error though. Because if it's manufactured with error, then you're basically either forcing your fins to go on slightly wrong, or you've made something where they can't all go on. And that is a caveat of this design. It would have to be something manufactured fairly perfectly. Probably us. We have composites has enough downtime, I feel, during kind of some sections. Yes.
But you guys know that you have to be.
Yeah. I was gonna bite the bullet on that one, probably.
Okay, I think you went to
Although now that you mentioned that, if somebody already has them, that's probably a better.
Every person who wants to be in washroom.
Yeah.
Needs to have washroom.
Yeah, okay, fair.
Yeah.
Yeah, I think I just answered like without thinking about it when you asked that, I'll be honest. Yeah, I will consider that. Well, what did you just ask me to go to? Yes.
So just a note for this, when you guys are sliding the tan piece on the green piece, it'll wear down that 3D print and also heat it up. So just keep that in mind, like.
Yeah.
3D prints, like, especially for layer lines are in opposite directions, they basically are gonna become sandpaper to each other. So, it is going to wear that down a little bit. Don't know if it's the end of the world, because it will say that green piece, but also
Yeah.
gonna do one for each.
That green piece also does not need to be actually perfect. It doesn't need to like perfectly fit in that slot. It can be fairly far away from any of the heat being generated, I feel. Like it doesn't need to be as tall as that gap is. I don't know, like what point you were expecting, like you're thinking like the most heat would be generated, the most heat would.
When the thing is getting sanded down, it's like clamped to a 3D printer.
Oh, you mean on like just the belt sander itself getting kind of hot?
Not so much the belt sander, the pin itself is gonna heat up from the sanding, and it's clamped to a 3D print, so like as long as you do a high.
Oh, do you mean the tan piece?
So the tan piece and the green piece, talk about pressure slide back and forth, just that they're gonna be basically friction sanding each other. But the orange piece being clamped to the pin is gonna experience.
Okay, yeah.
Yeah, I mean, it's not that big of a deal, it's just something to keep in mind when you're doing it, and like, maybe don't push it too hard between.
Okay.
Because they will.
Give some time in between, because we're doing 18 devils total.
Yeah, so maybe give it a chance to pull it down or something.
Okay.
It'll probably be fine, so.
Okay.
I'll stop now, because it's after 9.
All right.
Yeah. Cool.
So we do have lots of questions. They will be sent out,
Not just.
not just for you guys.
I hope so, I figured.
They will be sent out.